So good morning, good afternoon, and we welcome you to the Isaac Ikman Conference of Analysis in Developing Countries. And just to start with, let me leave you with Professor Enrique Vera from Universidad Pedagógica y Tecnológica de Colombia. Please.
Good morning. A special greeting to all the participants of this important mathematics conference. Congratulations to the three Colombian universities that support this conference: Universidad del Atlántico, Universidad Nacional, and Universidad Pedagógica y Tecnológica de Colombia, UPTC, in collaboration with Ghent University. Exalt the life of Professor Luigi Rodino of the University of Turin, who is an example future mathematician. It actually exalts the work of mathematician Richard de la Cruz, professor of the UPTC. I wish the joint mathematics project initiative between different countries. I wish you success in this conference. Enrique Vera, rector, Universidad Pedagógica y Tecnológica de Colombia, UPTC.
Okay. Okay, so after the words of Professor Enrique Vera, who are available in YouTube, we're going to start our opening ceremony. Just let me share the presentation. Okay, so good morning, good afternoon to everyone, depending on the place where you are located. We welcome you to the conference. The plan of the opening ceremony today is the following. First, we are going to hear some words of
Professor Dr. Uwe Keller, President of ISAAC, the International Society for Analysis, Its Applications and Computation. Later, I myself will provide some words. Later, we are going to hear to Professor Luigi Rodino from Italy, to whom we dedicate this conference, and later to Professor Fabio Nicola. So, starting with this program, I invite Professor Uwe Keller, President of ISAAC, to share some words.
Hello, everybody. As a student, if one would ask me about analysis in Latin America, the name would immediately come to my mind, of course, is Alberto Calderon. But if one asked me about something else, other persons, etc., I would have to start thinking about it. Later on, in my own field, I started working with persons from Mexico, Cuba, and Brazil, Venezuela. And I realized how rich and how diverse the number of persons are in Latin America who work in our field. And that one actually showed me how much it is, and often how much it is actually overlooked. And in fact, when ISAAC was founded, the original idea was that ISAAC should become something like an elite SIAM. But already at the first conference of ISAAC back in 97 in Delaware, 96 actually, one could see a lot of persons, mathematicians from Latin American countries appearing there. And in fact, a lot of our members coming from Latin America, but also from other areas which have several developing countries. In fact, the number of members we have from developing countries nowadays amounts between 1/3 and 1/2 of all our members. So one can see how active actually that developing countries are in the area of analysis. And in fact, no other part of our history actually shows it more than actually the time when Professor Luigi Rodino was president of ISAAC from 2013 to 2017, where we had 2 ISAAC congresses. The first one was in China, actually in Macau. And the second one was a highly successful ISAAC Congress in Sweden. And you could see actually the joining of these 2 ideas of having high-level research, high-level presentations, and so on, but also the involvement of persons who are not so much in contact with the mathematical world, at least at that time, but coming from countries where it was more difficult to have. Nowadays, we have all the technology, but originally, of course, if you would be in a country like, let's say, Nigeria or Guinea, it would have been rather difficult to come into contact. And that actually is what makes me so proud that we now have these kind of series together with IGNAM, where actually mathematicians can come together online and getting into closer contact, and which allows also people coming from universities which have not that big connections, like, for instance, universities in Europe and the United States usually have, and can see what actually is happening in our field. So that's why actually ISAAC was more than happy to actually having these conferences together with ICMA. And I can only wish all of you to follow these things, look at the talks, and enjoy the mathematics as well as the cultural diversity we have in our community. So thank you very much, and let's look forward to a successful conference.
Okay. Thank you very much, Professor Keller, for your inspiring words. So let me continue with the program. There are attendees First of all, I want to thank Professor Owe Keller, President of ISAAC, for all the support that he has given to ICMA Latin America over the last 2 years. This has been a very active year for our organization. We have established important agreements with different societies, such as ISAAC, to cooperate in organizing events like this one. Just a week ago, we held the ISAAC ICMA Conference of Women in Mathematics as a joint effort. In October, we also had the ICMA Latin America Congress 2024, and in June, we collaborate with Professor Enrique Suazua's group at Friedrich Alexander Universitat to organize the conference on trends in mathematical science. It was wonderful to see so many young mathematicians interacted with outstanding researchers. Among our speakers, we were proud to have Abel Prize laureate and Fields medalists, reflecting our commitment to providing excellent scenarios that inspire young mathematicians. This year, we worked hard to secure funding from the International Mathematical Union, EMU, for 2 of our projects. One of these projects focused on women in mathematics. It was even presented at the Chambers of Senators in Mexico, which showed the significant social impact of our work and our dedication to promoting inclusion and collaboration. Our goal is clear: to allow mathematicians from all the borders and geographical regions of Latin America to enjoy of inspiring mathematical experience. Virtual platforms and social media have been our main allies in achieving this. For the first time this year, our conference became hybrid events. In Colombia, the in-person program of ICMA Latin America 2024 was held at Javeriana University in Cali. Today, we are streaming this event from Bogotá and Tunja to young communities at the National University of Colombia and the Pedagogical and Technological University of Colombia, whose telecommunications department is broadcasting the conference live on YouTube. I would also like to extend my gratitude to the organizers of this event: Richard de la Cruz from UPTC, Tobias Castro from Atlantic University, and Santiago Correa from the University of Augsburg. Their dedication and hard work have made this conference possible. The support of ISAAC has been crucial in helping us to expand our initiatives from Latin America to developing countries, other developing countries, which is perhaps our biggest challenge after successfully organized our past ICMA conference. It is in this spirit, moved by the passion to share this message beyond our borders, that we are here today. After establishing the ICMA Latin America Prize, which was awarded this October to the distinguished Argentine mathematician Carlos Koenig, today we have decided to celebrate the mathematical career of another giant analyst in the field. We dedicate this conference to Professor Luigi Rodino from the Universidad di Torino. Professor Rodino is a distinguished mathematician known for his extensive contributions to mathematical analysis, particularly in the theory of pseudo-differential operators and partial differential equations. He graduated in mathematics from the University of Turin in 1971 and furthered his studies as a postdoctoral researcher at Lund University in Sweden under the supervision of Lars Formander, and at Princeton University under the supervision of John Kohn. Professor Rodino's research spanned a wide range of areas, including harmonic analysis, operator theory, and their applications. Professor Rodino is an exemplary mathematician. His work has reached the highest levels of the mathematical community. The very well-known Torino School of Microlocal Analysis owes much to his efforts, and his contributions to the theory of PDE, as we mentioned before, are invaluable. It is with great pleasure that now I invite Professor Luigi Rodino to take the floor as we honor him and his extraordinary career by dedicating to his mathematical life this conference. So, Professor Rodino, please.
Thank you for such kind words, and thanks for the organization of the Congress and for this not merited tribute that you give me. I would like to say some words about the continuing what the President Uwe Keller told now, some words about the activity of ISAC in favor of developing countries. But let me begin from the birth of ISAC. You know, ISAC was invented, by Robert Gilbert, who was at this moment also rector of Delaware University. And we are in the 90s of the past century. And I discussed with him and exchanged mails about what ISAC was and his motivations. Actually, he had, in principle, pure theoretical motivation. Say, he had a sort of competition with SIAM, S-I-A-M, Society for Industrial and Applied Mathematics. And he thought SIAM, you know, is a well-recognized association, was too much addressed to applied analysis, whereas it was worth to have an association devoted to, of course, also applications of analysis, but also to pure analysis. And this was at the beginning, but almost immediately, I would say that the aims did not change, but enlarged to an international perspective, and considering in particular developing countries. I want to recognize that this was merit of big merit for this was by Henrik Begeher from Berlin, who was the second president of ISAC. And say, almost immediately, he moved in the direction of developing countries, international perspectives, and I would say that this line was followed by all the presidents who came afterwards and till now. What I remember of the period I was president, and Begeher was still had still a role, was treasurer of the society, and he suggested me something that we did. You know that there was and there is a fee to enter ISAC, who was at this moment $300, and it was rather high. So we decided for people, say, from there is a ranking of the of salary, of year salary for each nation, and we decided to decrease for some people, say poor people from poor countries, to decrease to 50 euros the fee to register. I think you would ask me whether don't eliminate at all the fee for enter. It's a fee for all the life. Where you know that ISAC is a no-profit organization. As this was immediately what I liked very much about ISAC. We have no business affairs, say, but this small income due to the fees permitted us to permits at present as well to have a small treasure, very small treasure, and with this is mainly devoted to support in a small part as according to our limits, congresses in developing countries. So, and this is an action which is still continuing. But I want to say something more general about, developing countries. The fact is that from the mathematical point of view, developing countries got already development. I tell you, I am acting as editor of some journals, and I have a rather clear ideas what is going on in the publication, in the editorials, at least concerning mathematics. Say the US and Europe, who were the leaders in publishing, now are, well, did not decrease, but remained at the same level, whereas as number of papers, let's say this, or pages published in mathematics, and I think as well in other sciences, the landscape has changed drastically. Moving from east to west, I tell you who is publishing the most part of papers are China, also Vietnam, India, Iran, all the nations of the North Africa, and finally, South America, Latin America. Latin America, I think, will have an important role in this. Also, it is interesting to observe the net of collaborations I read in these papers. And developing, let's use this word developing countries, there is a very intensive net of collaboration between developing countries, whereas, old countries are somewhat isolated. This you can recognize immediately reading the present literature in mathematics. Finally, I want to say something about Latin America. You know, I am Italian, and my feeling is there in the sense that in the first part of the past century, millions of Italians moved in Latin America. In Argentina, more than half of the population is Italian from origin. And also, I have seen the past year, according to a statement of our national court, Italian court, they admitted at the Italian citizenship all the people mainly in South America, but everywhere in the world, having ancestors in Italian. Immediately we had more than 200,000 approved applications, mainly from Brazil and Argentina, but I would say from all the nations in South America. Okay, then thank you very much for this invitation. You know, you touch my heart in some sense, and have a good Congress. Congratulations to you.
Thank you very much, Professor Rodino. It was our honor to celebrate your mathematical career. So, in this spirit, then, I would like to invite Professor Fabio Nicola, maybe to say some words.
Many thanks to Professor Cardona and the other organizers for the opportunity to introduce Professor Luigi Rodino. I'll begin with a summary of his career and follow with some personal anecdotes. Luigi Rodino was born in 1848 in Cairo Montenotte, a small town in Savona province. His father was a physician during a time when practicing medicines involved great challenges. His mother worked as a teacher and liked writing. Luigi graduated in mathematics at the University of Turin in 1871. At the time in Turin, there were no experts in distribution theory, and Luigi acquired the basics of the theory through a course given by two former students of Laurent Schwartz, François Treves and Louis Boutet de Monvel, which significantly shaped his future path. In 1972, Luigi moved to Lund to study with Ormander, where he authored his first paper, a class of pseudo-differential operators on the product of two manifolds and applications. This paper was well received by the scientific community and can be considered an early contribution to the vector-valued pseudo-differential calculus, later carried on by Louis Boutet de Monvel, Alain Grigi, Bernard Delfer, Bert Wolfgang Schulze, and Richard Melrose and others. After a period spent at the University of Princeton with Joseph J. Cohn, Luigi Rodino became a full professor at the University of Turin in 1881. His research activity covered a number of topics, including the problems of hypoelectricity and locus solvability, the theory of pseudo-differential operators in the Gevrey category, and in more recent years, the global pseudo-differential calculus and time frequency analysis. During the initial phase of his career, he collaborated with Bernard Delfer, Cesare Parenti, Lamberto Cattabriga, and Luisa Zanghirati. Over the years, Professor Rodino has taken on several administrative roles at the University of Turin, such as director of the department, president of the mathematics program, and PhD program coordinator. He coordinated several national and international research projects and was president of the Isaac Society. At present, he is a member of the Accademia delle Scienze di Torino and a member of the working group of the Italian Mathematical Union dedicated to mathematical collaboration projects with the Global South. Alongside Cesare Parenti, he is recognized as the founder of the Italian School of Microlocal Analysis. In the early 2000s, he played a significant role in revitalizing this field by founding the Journal of Pseudo-Differential Operators and Applications with Ma-Wan Wong. His academic contributions include supervising 17 PhD students and authoring 6 books, along with approximately 150 scientific papers, receiving about 2,000 citations. And now a few personal anecdotes. During my freshman year at the university, I had the pleasure of meeting Professor Rodino while attending his Mathematical Analysis 1 class. His teaching instantly captivated me because of 2 key characteristics: exemplary clarity and a constant hint of irony. Attending his lectures was indeed a pleasure. Subsequently, I took his course on partial differential equations, which was in fact inspired by the above-mentioned course given by François Treves and Louis Boutet de Monvel. Throughout our numerous scientific collaborations, I spent many hours in his office. At the time, Professor Rodino had numerous students and collaborators. Entering his office felt akin to a doctor's office. Reservation was recommended. The community spirit in his research group was fostered by annual lunches he hosted at his country house, where he invited his students and close collaborators. Over the years, I have come to value various traits of Professor Rodino's personality, especially his great generosity in sharing ideas, his warmth, and naturally his extensive mathematical expertise. I've been particularly impressed by his constant concern for young researchers facing difficulties in getting a permanent position. Also, I like to recall a kind of poster displayed on his office door, reading Elogio della mitezza, namely praise of meekness, alongside a picture of a cat. I believe that meekness truly defines his interactions with other people. In conclusion, some acknowledgements. On behalf of his former students, I would like to express gratitude to Professor Rodino for being an exceptional master and mentor, for his generosity and friendship. I also thank Professor Cardona and the other organizers of this lovely tribute. I wish this conference great success and extend my best wishes to all participants. Thank you.
Thank you very much.
Thank you, Fabio. Thank you very much.
It's very nice to see how much the mathematical career of Professor Rodino also touched other mathematicians. Okay. So just then to finalize our opening ceremony, just let me remember that we are going to start our scientific program today in 20 minutes at 3 p.m. in Central European time. And we continue with the plenary session of Professor Luigi Rodino. So thank you very much to all the attendees for being here. Thank you very much to the organizers. I remember the name of the organizers, Richard de la Cruz from Universidad Pedagógica y Tecnológica de Colombia, to Tobias Castro from Universidad del Atlántico, Atlantic University, and to Santiago Correa from the University of Augsburg in Germany. Also, all of them are part of this hard organization. So thank you very much, and see you in 20 minutes.
Alexandra, te pregunto. En este momento
Listo? Okay, so it's my great honor then to introduce our first speaker of the conference, Professor Luigi Rodino from the Università di Torino. And also, it's nice to see that Professor Elena Cordero is joining us also to handle the technical things related with the talk of Professor Rodino. So Professor Rodino will talk about beginner kernels of operators, applications to the Schrödinger equation. So Professor Rodino, you can start. And thank you, Professor Cordero.
Thank you very much. Professor Cordero, beside being technical help, is also collaborator of this paper as well. Maybe go to the next slide with Gianluca Giacchi.
Excuse me, I'm not, it is not changing the slide, so maybe I cannot change.
Elena, scusa, hai schiacciato CTRL L?
CTRL L.
Perché CTRL L lo mette a schermo intero. Per qualche motivo non lo mette a schermo intero.
Sì. Il problema è che non cambia. It doesn't change the slide. Don't know why.
Prova a cliccare sopra ancora, sopra la presentazione e poi riprovare. Non va.
No. Sorry for video setting. No, the fact that it does not.
Puoi schiacciare, credo, la freccia in basso dove c'è a sinistra, in basso dove c'è 1.41 e poi le due frecce, potresti provare con quelli.
I'm trying, but I'm not allowed to move. No, maybe because. Okay. Just a second, if I'm able to. Let me just, sorry Luigi, and sorry to everybody.
No,
I'm
okay.
Trying to understand how to share. Okay, the document is this one.
Tu Gianluca sei in grado di proiettare tu stesso?
Sì, devo prima
vediamo se Elena riesce.
le...
Vediamo un po' se Elena riesce.
Yeah, because no, the fact is that one should be able to say.
May I suggest something? Can you send the presentation to the one, and the one just shares the presentation, maybe? Okay,
but the fact is, it doesn't change. I share the screen. Maybe so it is not the right way of sharing. I mean.
One, you're mute.
Okay. When you select sharing a screen, you choose the window. You choose the window, or
yes,
entire screen. Maybe entire screen, and later.
entire screen, but then entire screen, what? I don't see. No, the entire screen does not allow me to.
Okay.
No,
Oh, now it's you.
Now it's working. It was working.
it was working.
It was working, yes.
Really? So entire screen, and then no, it's not.
Okay, then maybe we can go for Santiago's suggestion. If you want, you can send me the slides and then I can.
Yeah,
Maybe, yes, I can
better.
send you in a couple of minutes. I send to Duvan the slides, and you project the slide, Duvan.
Exactly.
I'm sending them.
Maybe to Duvan.
I'm trying to.
to Duvan the slides, Elena.
Yeah.
Yeah,
But now it's
sharing
working.
now.
Okay.
Now,
Gianluca,
now we
you are sharing, right, Gianluca?
Can you see it all screen?
We can
Yes,
see you.
yes.
We can see, yes.
Okay.
Can you try to move the slide, Gianluca?
Yes,
Okay.
It's working excellent. Thank you very much.
you can base on Gianluca. That's okay. We
Okay,
go.
Maybe then let me introduce Professor Rodino again. Surely it's my great pleasure then to introduce again Professor Luigi Rodino from the Università di Torino, who will talk about Wigner kernels of operators, applications to a Schrödinger equation. So thank you, Gianluca, and thank you, Professor Rodino.
Please go to the next slide where you both appear as you are co-authors. Actually, Elena prepared the slides. Thank you very much. Most part of the work is due to them. I think we can go to the next slide where this is not our collaborator directly, but it is in this talk is our hero, is Wigner. Wigner, who invented the Wigner distribution or Wigner transform, if you want, in the 1932. Wigner was from Hungary, then moved in Germany, and then moved in US, in Princeton, where he remained till the end of the past century, very active. And the paper, look, was written in the 32, a lot of time ago. Wigner belongs to this number of people inventing quantum mechanics. I cannot describe you. It is written too small, but doesn't matter. We are not looking to, and later I would be able to describe you the physical meaning of a paper. But if you go to the second page, next, here Wigner, aiming to solve the physical problem, proposes the Wigner transform, and in the next 3-4 pages, he wrote what now is contained in 20 pages, usually in textbooks. Here also is too small to read. I propose to go to the next slide where the Wigner transform is written more in detail. Actually, I would suggest, as Wigner did, to think this G equal F in this expression 1. You recognize a Fourier transform. Fourier transform of a function f times g depending on x and y in the integration variable. So looking now to the Wigner transform, we recognize some very modern ideas, which are, say, micro-local analysis. What we want is to detect frequencies appearing at a certain x time or space fixed variable. This is actually a fourth step. This is not in the landscape of Fourier, say. Is in the modern landscape of quantum mechanics and signal theory also. For Wigner, actually, taking, I told you, G equal F, the aim is to do a micro-local analysis of the wave function solution of the Schrödinger equation. The micro-local analysis, it is a simultaneous density of time and moment, say space and momentum in this case. Let me spend till a moment to compare with a modern point of view. We do not write as in one, as in this formula, the micro-local analysis of a function f. Rather, we integrate fy times g moved, translated at the space value x, and then localize at x, the result. So it seems, it looks somewhat strange, say, somewhat surprising the way how Wigner localized, micro-localized the function. And actually, this is one of the first, maybe the first idea of micro-localization. It is somewhat strange, but because the function f, as I told you, g is assumed to be the same f, is localized by f itself. From the historical point of view, at this moment, we are in 32, cutoff functions did not exist or were not realized as now. And so, cutoff function was f itself, and then for symmetry reasons, the translation was split into the two factors. But the deep motivation, there is a deep motivation that this micro-localization is wonderful for the analysis of the Schrödinger equation. Now, Gianluca, we can go to the next formula in the page here. The idea, it is a general spirit of micro-local analysis. You have an operator. In this case is the Schrödinger propagator. You start from the micro-local analysis of a function, of the initial datum of a function, and then you want to relate this directly, immediately to the micro-local analysis of TF, of the result, without spending time on TF. Yes. So what we want to do, what we did in this series of papers was to reconsider from a modern setting, functional analytic setting, the ideas of Wigner and possibly generalize to more general Schrödinger equations. I think we can go to the next. Here is the Schrödinger equation which we study. The Hamiltonian AXD will be a quadratic form in x and psi, whereas BXD is a bounded potential, but it is in general a pseudo-differential operator. in the class S000 of Ormander. Maybe we should return later on a precise definition of a pseudo-differential operator. As for the Hamiltonian, it is a classic Hamiltonian, quadratic Hamiltonian. Maybe the next slide contains some examples. Only minus delta is the free particle if potential is missing. And second and basic example is the harmonic oscillator. Again, assuming the bounded potential 0. Third example is a general quadratic Hamiltonian plus a potential depending on the x alone. But let me return to the first, stay there. Say, we want to start, what we do? We want to start from a solution of a Schrödinger equation already expressed in some form. Say, nowadays we have a lot of ways, possible ways to write down the solution of a Schrödinger problem we wrote. Maybe the easiest is the solution by semi-group theory. A solution exists and is unique in L2 or Sobolev spaces, etc. How semi-group theory does not give to you a very clear expression of how is the propagator, and we would like to have something more explicit to work on this. And then we can go to the next slide. We can use this formula as reference. We give Bernard Delfer and by Fourier integral operators FIO of type 1, because there are other different expressions, say. This is maybe the most elementary. Where phi is a quadratic form, regularity of S is related to B. Now, maybe let's go on. Gianluca, okay. Here, I cannot recall you all the construction of this solution, but let me say that the basic step is to solve in classical terms our physical problems, that is, consider the Hamiltonian flow. Then in the formula 2, the phase function phi is strictly connected to the Hamiltonian flow. Say, solve the Hamiltonian flow is a nonlinear problem. So maybe if you want, this is the difficult problem. In general, it is a very difficult task. In the linear case, that maybe was in the next line, it appears. Yes, it is a little more easy. Then, once you have the Hamiltonian flow, you immediately detect phi by the phase by an integration and vice versa, However, let me begin to emphasize a limit of expression 2 by Fourier integral operators is that the Hamiltonian flow, under our assumption, exists for all times, whereas the phase function, you have to do an inversion when computing phi. It beats some problem, which are maybe as explained in the next slide, in the linear case. This is, for simplicity, let's fix time, t equal 1. Then, to be explicit, the relation between the phase and the Hamiltonian flow is expressed by this. S there. And this is much more explicit of what I was saying before. Once you have S, that is the Hamiltonian flow, you compute immediately phi in this way. So you realize there, if the A, block A, in the expression of S, is not invertible, you have problems when writing phi, because you have A minus 1. So there's a limitation. Once you have a time dependence, starting from t equals 0 and for a while, A is invertible. At a certain moment, we call caustics. Caustics have different meaning in mathematical physics, but say when A, t, depending on t, is not more invertible, the expression before fails by FIO. Let's go on. This is well explained by two examples. This is the free particle. Let's look at the end of the page. There is ST. The block A is always the identity. Always the identity, so is always invertible. You have no problem. You apply, if you want, the formula in the preceding page, and you have this phase function. So everything works. But let's go on to the next. In general, FIO representation does not hold for every t. The basic example is the harmonic oscillator. I think here representation is too general. I would suggest you to eliminate x1 from the picture. So you have the standard harmonic oscillator. So the Hamiltonian flow is not written there, but is RQ. You move around circles, say. So it's well defined that you go to time infinity running around with circles. But let me look to the expression of the phase function. The next line, the final here, you know, when you write down the phase function, 1 over cos t appears, tangent is sinus over cosinus. Again, for t equals 0, it's okay. And for a while, it is okay. No problem. When you arrive to pi half, you have a problem because this is 0 and this expression fails. Okay. Now, I think this is, for the moment, I will skip this. Is in short, but let me comment a moment. The work of around 10 years ago, in collaboration with Fabio Nicola and Charlie Grökenig, where we studied this problem by the short time Fourier transform Gabor matrix. But I will return in a moment to this. Gianluca, okay, we go to the next. Now, to prepare our revision of Wigner work, we have to set things in the modern language. Say, Wigner used L2. L2 is perfect, but let's approach in a somewhat more general form. Nowadays, we have distributions that didn't exist at that moment. Take, in general, let explain what is the Wigner kernel we want to study. Let be a linear bounded operator from S to S prime. These are the Schwarz spaces of test and distribution functions in Rn. Then we define the Wigner kernel in this way. little more detailed than considering G equal F. But Gianluca, let me project all the page and go to also where is the theorem. I would prefer to start from this theorem. The Wigner kernel is the Wigner transform of the Schwarz kernel. According to Schwarz, every linear operator is representing from a kernel K, T, XY. XY are the variables. We do the Wigner transform of the classical Schwarz kernel. This adds the dual variables psi and eta frequencies, localized frequencies at x, y. There is a minus eta appearing for technical reason, say. Well, this is maybe I would refer to the center line where we adopt actually the cross Wigner, but I would say take G equal F, then we do what I announced. We start from the Wigner of F, we apply our Wigner kernel operator, and we arrive immediately to the Wigner of TF. And the functional setting is very nice in the sense that you can use S prime, and as well L2. Okay, this is the functional definition. Yes, you can go to the next. Yes, I was a little too short speaking about the pseudo-differential operators. Are defined here as standard. Say for non-experts, if the symbol sigma that you see in the first line is not depending on psi, then this is just a multiplication operator. If sigma does not depend on x, sigma psi, this is what is called the Fourier multiplier, that is a convolution operator. If you do the Fourier transform, you have a convolution operator. In general, the kernel is given by the Fourier transform with respect to the second variable, where you put y minus x in the outcoming result. Let me, a natural question that would be the first step is to consider Wigner kernel for pseudo-differential operators. This is rather unoffensive, easy, in the sense that this was the first work, maybe of some years ago with Cordero. And what you obtain is not a kernel of a not a pseudo-differential operators in the same class. And then in some way, there are no problem of moving microlocal singularity. It's the easy case, say. Let's go on. I think here we are already to say to the main theorem. Here, for the moment, t, the variable t does not appear. Let me say that our aim is then to describe the Wigner kernel of Fourier integral operators and solve this annoying problem of the caustics, say that it appears in the FIO representation. Well, for the moment, in this statement, let's assume T is fixed for simplicity. Then the first result is the following, that remember S is was the Hamiltonian flow related to a quadratic form. That is, now it is a linear symplectic transform. So phi is a quadratic polynomial and CS is related canonical transformation. We are arguing at a fixed time t at this moment. Then the result is the following, that in some sense we are reduced to the easy case of a pseudo-differential operator. The Wigner kernel is the kernel of a pseudo-differential operator that is in the same class as 000, but in dimension 4D. And but at the beginning, entering on the initial variables, it's linear, the linear change of variable S exactly corresponding to phi. Maybe some comment, assume, okay, if phi, the phase function is x times psi, then you have a pseudo-differential operator, and this S is the identity. Other example is sigma equal 1. Then only phase, the phase function appears. Then in this case, the pseudo-differential operator related to H is very simple, is the identity. So the H, the kernel of the identity is the delta on the diagonal. You would get Z minus SW. That means, I would say that this was the original idea of Wigner. For the moment without time dependence, that if you start from the Wigner representation of the initial datum of the function f, then you compute, we want to express the Wigner representation of Tf, it will be the solution at a certain time of the Schrödinger equation. This is simply obtained by a linear change of variable on the Wigner transform of the initial datum. So I think I don't know exactly how Wigner invented this. He attributes to some friend of the idea, but you, of course, this is comes out from computation, but the difficult thing is to find the correct definition that he did. Okay, we can go to the next line. This first step without time t, say, has led us to, as usually mathematicians do, to present elegant theory, let me say. That is, to generalize the class of the Fourier integral operators, defining them as the operator whose kernel is given by the kernel of a pseudo-differential operator with the same linear composition. Look that this is more general because not all the H are obtained as in the preceding framework of FIO. And then, basing on this definition, but it is not only a matter of elegance, but this theorem has a good future that I will explain you in a moment. That this larger class is an algebra adjoint, containing adjoint and compositions. Note that FIO of type 1 are not an algebra. So we have to enlarge this. And very interesting, this, there is the Wiener property, that the inverse is in this algebra. I have not explained to you exactly this, but in numerical analysis, this is important. It means that you can limit computation near the diagonal in some sense. Okay, we can go on, and now we return to the initial problem of the Schrödinger equation, and we solve the caustics problem as well. What we were not able to do with standard FIO. Now, in this larger class of FIOs, we are able to state that the propagator belongs to FIO corresponding to the linear symplectic change of variables depending on t, that is the Hamiltonian flow computed on the quadratic Hamiltonian. So the Wigner kernel has an expression of this type where HT is the kernel of a pseudo-differential operator as before, depending on t continuously. Remark important that requires a little proof is that, and we enjoy of a preceding remark on the algebra, no problem with caustics. That is, the representation with phi O is would limit in principle the statement to the interval, say 0 pi half for the harmonic oscillator. Whereas what we state here is that this is valid for every t. I think we can go to the proof. I think there is the proof. First step is that for small time there is this expression st. But then we do a standard trick, that is, once you arrive a little before arriving to the caustic, you take as initial datum the value you have reached at this moment, you apply again. Say you can do this with FIOs as well, but you obtain a composition of FIO of type 1, which is an integral which is growing as number of variables. So the expression is not so nice. Whereas here, thanks to the fact more or less obvious, we can project, we can show the next lines. The fact is that the Hamiltonian flow has the semi-group property, the group properties, then you glue every time the preceding piece of S with the next, and you have and you use the fact that our larger class of Fourier integral operators are an algebra, and you get a global solution. Okay, I think this is what we like to prove, but now there is something interesting. We can go. For the moment, I ignored this page with Wigner kernel. Wigner kernel is the same type of arguments, but with Wigner transform replaced by short time. And so we wrote a series with Cordero, Grögenig, a series series of papers on that. And the expression of the Wigner, of the Gabor matrix, when you argue on the short time, is given by this expression that you read in green in the 1 to 4th line square. So we noted this basic fact that once you have the Wigner kernel, by the smoothing, by convolution with a smooth function which is given by this Wigner G, etc., but in practice you can take as G the Gaussian, you convolve, look to the last line in green. You take the Wigner kernel K, you convolve, do convolution with a Gaussian, and then you obtain our old, say, short time kernels squared. Note that Wigner kernel could be with rough expression containing some delta or also ghost frequencies. Convolving with the Gaussian, you smooth up. You eliminate all these discontinuities, delta, etc. But you keep what it is interesting in our situation, or is the behavior at infinity. The behavior at infinity is kept. And so, by this last line, in principle, we recapture from Wigner kernel the results of some papers we wrote in the past concerning the short time Fourier transform. Okay, now to explain, it is worth to explain this in somewhat more detail, the relation between short time Fourier transform, which is written here down in the footnote. In the footnote, you know that it seems much more natural to microlocalize the short time Fourier transform. The relation between short time and Wigner was already established long time ago, say 40 years ago or similar, by Husimi and by also, let me mention, Leon Cohen, that if you convolve the Wigner in this formula 7, take pi the Gaussian, yes. You convolve the Wigner of a function with the Gaussian, you get the short time to the squared. This 4 refers the note to the footnote. So, in some sense, what we wrote before for the Wigner kernel is the kernel version of this Husimi argument. There is an example here. Take delta tensor 1. Take delta as function, the delta function. Delta function, from the point of view of signal of quantum theory, means that in space variables, you are concentrated at the origin. As frequencies, all the frequencies are present. And so, perform the Wigner of the delta is equal delta tensor 1. That is, delta means that you are concentrated as space variable at the origin. 1 means that all the frequencies are present. Figure 1 here, of course, we cannot represent the delta by a picture, but this is what we can do, is the representation of the Wigner of the delta. You know, where the variable x in the picture in the left is small x in sphere, you are concentrated there, and all frequencies are equally present with 1. Okay, let's compare with the short time The short time of the delta is written the second line. If you take, again, phi, for short, we write phi instead of the Gaussian. The Gaussian, the short time with window Gaussian of the delta is the Gaussian itself. But look, the variable xi is missing. That is, it's a Gaussian concentrated at psi x equals 0. X equals 0 and independent of psi. So if we apply the Usimi formula that it is written in short, applied here in short here, it turns that what we expect, that convolving delta tensor 1 Wigner of delta with the Gaussian, Wigner of the Gaussian is Gaussian in a double number of variables. You obtain the square. And we have a picture for this, and we can, this is the Gaussian in the x variables only. That is the preceding picture after smoothing. This corresponds exactly to the relation, as I told you, between Wigner kernel and short time Gabor kernel. But of course, pictures for kernels are impossible because we are in dimension 4. Dimension 2, say you can maybe fix some variables. This is acceptable, more reasonable. I think we are at the end. The next slide is the. Let me explain a moment the by the references there. I think fix attention first on these in blue are the old references on the short time kernel. Maurice de Gosson for symplectic analysis. Elfer was mentioned. The original paper of Wigner's in 32. And concerning the new papers, I would suggest you to go to arXiv. Nowadays, this arXiv is dominating. You go there and look for Elena Cordero, and you find all the papers related to this. Yes. Okay, we may project the last slide. Thank you for the kind attention. Thank you to you, Gianluca, also.
Okay, thank you very much, Professor Rodino, for your very, very nice talk. So at this moment, we are open for questions. Are there questions for Professor Rodino? Can you hear me? Are there questions for Professor Rodino? I think people was happy with your presentation, Professor Rodino.
It was satisfactory.
I myself, I have a question, right? Because in this model that you present and the propagator is this Fourier integral operator, right, with a symbol which belongs to this class, Hormander class of order 0 and 0, 0 type, right? But still the phase is real value, right? Still the phase is real.
Yes, it should be told that everything is a real value. Yes.
Right. My question, because also I am interested in Fourier integral operator with complex value phase function, is have you considered also the case where the phase is complex, or have you know a model of interest where the phase being complex could be interesting?
We have not considered till now complex phase. It would be very interesting. Of course, you put the limitation on the imaginary part in such a way that the easy presentation, the easy problem, easy. Some natural problem is to assume the imaginary part is such that the integral is convergent. Of course, it's very interesting, starting from Hamiltonian flow and etc. I know there are many papers for Fourier all the papers on Fourier integral operators with complex phase function. I remember my friends say Sjöstrand and Melin Sjöstrand, and then Brudzinski, my friend.
Yes, I learned from the book of Professor Luczewski.
And your friend.
My advice, yes. That's true.
Yeah.
Okay. Does anyone has another question for Professor Rodino? Okay, I think people was.
Maybe one question I have.
Okay, Professor Luczewski, please.
Yes. Yeah. So, hello, Luigi.
Hi.
Yes. Maybe so. The faces you can cover these faces which are only of this form, or more geometric description.
No. We have now a paper. Maybe it will go in archive with today. Elena is writing where we treat say homogeneous second order homogeneous smooth phase functions, but the situation is much more difficult in the sense that the pseudo differential operator H, if you start from S000 and you follow our statements, the pseudo differential operator appearing is very strange in some exotic class. So there is a drastic change. Say in this week, it will appear in archive a paper on that.
Okay. Yes. Thank you.
Thank you.
Okay. Thank you very much, Professor Luczewski, for your question. Okay, Professor Rodino, once again, thank you very much for accepting our invitation. We also invite you to enjoy our scientific program of this conference that was organized to celebrate your mathematical life.
Thank you very much to you. Thank you very much to all of you.
So we are going to start in 4 minutes the talk of Giovanni Girardi.
So good afternoon. Do you hear me?
Yes, we can hear you. Yes.
Okay.
Hi, Giovanni. Hi.
Hi. Nice to meet you.
Hi.
So I try to share the screen, maybe, right?
Right. Yes, please.
Can you see it?
I can see your screen. Yes.
Okay. So
I can see your screen. Maybe, do you want to try to move your slides from one slide to another one? Perfect. We can see. And it's in full screen mode, so it works. Perfect.
Okay.
Thank you. So let's start in 3 minutes, Giovanni.
Okay. Thank you.
Thank you very much. Entonces, Alexandra, ¿cómo estás? Muy bien, Alexandra. Entonces, vamos a iniciar con la charla del profesor Giovanni Girardi en 3 minutos. Muchas gracias, Alexandra. Okay. Okay, so the technical support of the technical support says that we can start. So it's my great pleasure to introduce our next speaker, Professor Giovanni Girardi, who will talk about critical nonlinearity for some evolution equations with Fujita-type critical exponents. So, Professor Giovanni Girardi, thank you very much for accepting our invitation. Please start.
Thank you. So first of all, I want to thank the organizers for this nice invitation. It's a pleasure for me to give a talk during this Congress. So I will present recent results which I published in a recent paper on nonlinear differential equations and applications. In particular, this is a continuation of a project, of a joint project with Professor Reisig from University of Freiburg and Professor Hebert from Sao Paulo University in Ribeirão Preto. So in this work, I considered the Cauchy problem for this general nonlinear partial differential equation. So in particular, you see that on the left-hand side, we have a linear differential operator, which is of order m in the time derivatives. And in front of each derivative of order j with respect to t, we have an homogeneous differential operator with respect to x. It's homogeneous of order rj, so of course it could also happen that for some j this pj is equal to 0. Instead, on the right-hand side, we have a nonlinear term. This nonlinear term is the product of a power type nonlinearity, so modulus of u to the power of p, times a modulus of continuity applied to the modulus of u. So here the power p is greater than 1, and let us recall what is a modulus of continuity. A modulus of continuity is a function from 0, 1 to 0, 1, which is continuous, is 0 in 0 and 1 in 1, and it is also concave and strictly increasing. So, first of all, in the case in which the nonlinearity is just a power nonlinearity, so without any modulus of continuity, so formally in the case mu equal 1, we will provide a constructive method which, under sufficient conditions on the linear differential operator L, allow us to evaluate a critical exponent PC for this model. By critical exponent, we mean that for p greater than pc, we are able to prove the existence of a global in-time small data solution. So assuming the initial data to be sufficiently small in suitable functional space, we are able to prove the existence of a global in-time solution. On the other hand, if p is less or equal to pc, we are able to prove the non-existence of global in-time weak solutions. We will see later in detail the meaning of weak solution for us. Then, fixing p equal to pc, we will discuss a critical condition on the modulus of continuity mu, which allow again to determine a threshold in the global existence result. In particular, we will determine an integral condition on mu, such that if this integral condition is satisfied, we are able to prove again the global existence of small data solution. Instead, if this integral condition is not satisfied, we can prove that no global in-time weak solution to this problem exists. In particular, it is interesting to discuss, but this is still an open problem, how really this condition depends on L. I will explain you better in the next slides. So before giving you my main results, I want to explain at least why we discuss such kind of problems. So in the literature, you find many authors which consider several different choices of the linear differential operator L in this general form. And first of all, they discuss some LP-LQ long-time decay estimates for this problem. So assuming the initial data F to be in some LP space, they investigate for which Q we can be sure that U is in LQ, and in particular how the LQ norm of the solution, or also some of its derivatives, decay when t tends to plus infinity. Then these long-time decay estimates, by applying some Banach fixed point argument, can be applied to study some existence result for the corresponding nonlinear problem with the power type nonlinearity, modulus of u to the power of p. So again, many authors in this case investigate the existence of a critical exponent according to the definition which I gave before. So for p greater than pc, we have the global existence. For p less than pc, we have the non-existence. The critical case p equal pc is sometimes in the global existence range, sometimes in the non-existence range. But we have now in the following, we will be interested in the case in which we have the non-existence also in p equal to pc. We will see. So a typical and important example is the following. This is the classical damped wave equation. What is known from this from a paper of Matsumura of 1976 is that the solution to this damped wave equation asymptotically decays like the solution to a corresponding heat equation with suitable initial data. The reason is that the presence of this damping term ut produces what is known as a diffusion phenomenon. So this means that asymptotically the solution to the damped wave equation behaves like the solution to the heat equation. In particular, if you consider the LP norm of the difference of u and v, this decays faster than the LP norm of v for all p between 2 and infinity, under certain assumption on the dimension. So, okay, this means that the principal part of u behaves like the solution to the heat equation. And so, as a consequence, if you consider the corresponding nonlinear problems, these two problems have exactly the same critical exponent, which is the well-known Fujita exponent. So if you consider p greater than Fujita, which is 1 plus 2 over n, then one can prove the existence of global in-time solutions, for instance, assuming small initial data in H1 times L2. Instead, for p less or equal to Fujita, assuming this sign condition on the integral of the sum of the initial data, one can prove the non-existence of global weak solutions. So there are several papers in which these results have been discussed. For instance, in this paper by Todorova Giordano, it is considered the case of compacted supported data. Instead, okay, in this paper by Zhang, the non-existence result is proved. So what we understood is that, in particular, from the previous slide, if you take p equal to Fujita, under this sign assumption, we have the non-existence. Instead, if we take Fujita plus epsilon, we have the existence of global solutions, small data solutions. So our question in this paper with Ebert and Reisig was the following. Is it really necessary to take Fujita plus epsilon in order to have the existence of a global solution, or is it maybe sufficient something less? So for this reason, we fixed the exponent equal to the critical exponent, so the Fujita exponent, in the classical damped wave equation. And we multiplied this power nonlinearity by a modulus of continuity. Again, I already recalled the definition. As an example of modulus of continuity, you can consider a function which is continuous, which is 0 in 0, and for s sufficiently small is equal to minus the logarithmic of s to the power of minus alpha for some alpha greater than 0. Or also, you can consider still a function which is continuous, which is, okay, concave and straight increasing also, which is 0 and 0, and for s sufficiently small is equal to the iteration of some logarithm. So in particular, the last logarithm s power minus alpha, still with alpha greater than 0. So what we proved in this paper is that least in space dimension n equal 1 and 2, if the integral from 0 to k of mu s over s in the S is less than infinity, or k arbitrarily small, then one can prove the global existence of small data solutions. Instead, if this integral is infinite, then one can prove that no global weak solution can exist. So if you think to the previous example in which you had mu of s equal to minus the logarithmic of s to the power of minus alpha, at least in a small interval, then you have that for alpha greater than 1, you have the global existence of small data solutions. Instead, for alpha less or equal to 1, you have the non-existence of global weak solutions. So, as you can see, we found here a critical condition on mu. So it seems that if one wants to investigate the critical nonlinearity for this problem, it is too rough to consider the set of power nonlinearities. One should consider power nonlinearities, time, and modus of continuity, because also in this set you still find a threshold, so a critical condition on mu. So my idea was to try to understand, okay, this result was true in the case of a classical damped wave equation. What happens instead if you consider a more general different linear differential operator? So again, for this reason, I consider this general case. For simplicity in this presentation, we assume that all the initial data are equal to 0, except for the last data, which is equal to a certain f. And again, on the right-hand side, you have a power type nonlinearity times a modus of continuity. So first of all, we need to fix p equal to the critical exponent. So we need a constructive method that, at least in some cases, and this will be true when the critical exponent is determined by scaling arguments, so it is a Fujita type critical exponent. So in all these cases, we can give a constructive method which allows to write explicitly what is PC. Okay? And then once we have determined PC, the idea is to fix P equal to PC and determine and investigate which is the influence of the modus of continuity on the existence result. And again, we will try to discuss, but again, this is still an open problem, how this critical condition depends on the linear differential operator L. We will see, I can say already now, that when we have a Fujita type critical exponent, so this is the critical exponent is determined by scaling arguments, we find exactly the same integral condition which we had for the classical damped wave equation. Instead, if the critical exponent is not determined by scaling argument, like in the wave equation, for instance, without any damping, in this case, it seems this seems not true. So the critical condition seems to be different. Okay. So first of all, in order to discuss these questions, we need to give a definition of weak solution. So for simplicity, we fix also Pm equal to 1 and Rm equal to 0. In this way, we can write the linear differential operator in this form. So now, assume that the initial data is in L1 lock, and we fix in general t greater than 0, between 0 and infinity. So we say that a function u, which is LPC lock both with respect to t and with respect to x, is a weak solution if it satisfies, of course, all the initial conditions, and moreover, for all test function psi, which is C infinity with compact support in the interval 0t times Rn, and which is equal to 1 in a neighborhood of 0, you have this integral identity. Here, this f of u is exactly the nonlinear term. So in our case, modulus of u to the power of p, of pc, times the modulus of continuity. What is this integral identity? In practice, is the integral identity which you get if you assume that U is a classical solution and you apply integration by parts. So it's exactly the same identity which you get in that case. So this is now our definition of weak solution. And now we want, again, to give a constructing method for the critical exponent PC. This, I repeat, is not doesn't work every time for each L, but works when the critical exponent is determined by a scaling argument. So it is a Fujita type critical exponent. So which is the idea? First of all, we define this set J, which in practice tell us which are really the times derivatives which appears in the operator. So is the set of the indices J such that Pj dx is different from 0. So in the equation you really see the derivative of order J. Okay. And then we introduce this function G, which is which associated to each eta in 0 infinity, the minimum over this capital J of J eta plus Rj. So this means that okay, for all J in J, you evaluate J times eta plus the order of the homogeneous differential operator Pj. Okay. And moreover, you define age function from 0 infinity to R such that age of eta is equal to 1 plus g of eta over n plus eta minus g of eta positive part. So in particular, if this denominator is negative or equal to 0, as you can expect, age of eta is equal to infinity. And then we define PC equal to the maximum of this age of eta, where eta belongs to 0 infinity. Okay, in particular, we will be interested and we will give our main results in the case in which PC is strictly greater than 1 and less than infinity. This is the interesting case for us. And what is important and will be useful then in the proof of the main results is that if PC is greater than 1 and less than infinity, then for sure there exists one eta bar between 0 and infinity, so strictly greater than 0 and less than infinity, such that PC is exactly equal to age of eta bar. So this means that this maximum is obtained exactly in this eta bar, which is greater than 0 and less than infinity. Moreover, I want also to underline one other thing. Since we are supposing that PC is strictly greater than 1, this means
Creo que se silenció.
Sorry? Excuse me, I think there is a problem. Can you please unmute your...
do you hear me?
Yes, perfect, thank you.
Okay. But did you lose some minutes or just?
I think it was only the last slide, so you can
okay.
just resume there. Thank you.
Okay, so I was explaining how to obtain this critical exponent PC, at least under sufficient.
Giovanni,
It's happening again.
No, why? I don't know why the microphone turned off automatically.
okay.
I don't know if it depends on me.
Maybe can you try to continue? Let's see if it works well now. Sorry.
Okay, let's try. So I was explaining how to get this constructed method. So we define this set J of the derivatives which really appear inside the equation. So in particular, J belongs to capital J if in the equation you have really the derivative of order J. So this means that Pj is different from 0. Then we define this function g from 0 infinity to r, such that for each eta, g of eta is the minimum of j eta plus rj, where I recall rj is the order of the homogeneous operator. And then for each eta between 0 and infinity, we define age of eta equal to 1 plus g of eta over n plus eta minus g of eta, positive part. So this means that if this quantity is negative, of course, we will have age of eta equal to infinity, negative or equal to 0. Okay? And then we define Pc equal to the maximum of age of eta with eta between 0 and infinity. So what I want to underline is that in the following slides, in the following results, we will assume that Pc is between 1 and infinity, so avoiding both 1 and infinity, at least in the first part of the presentation. And in this case, one can prove, it's not so immediate, but one can prove that there exists some eta bar between 0 and infinity, such that Pc is exactly equal to age of eta bar. So this means that this maximum is reached in some point which is inside the interval 0 infinity. Okay? So in particular, it's strictly greater than 0 and less than infinity. Moreover, another important remark, which will be useful in the proof of the non-existence result, is that if Pc is strictly greater than 1, you can be sure that this linear differential operator does not include any zero-order term. So you don't have derivative of order 0, you don't have any constant in practice in the linear differential operator. Indeed, if you have j equals 0 in the set capital J, and also rj equal to 0, this means that you understand this minimum always assumes value 0 for each eta, and then this means that this age of eta always assume value 1. So in this case, the critical exponent, when you have a zero-order term in L, the exponent Pc is equal to 1. So in the following, we will assume Pc greater than 1. This implies that you have no zero-order term in the equation. I want to underline that this procedure was not introduced really by me, but by myself, but just generalize an idea of Dabicco and Fujiwara in a paper of nonlinear analysis, in which they in particular consider Pj, which are fractional or integer powers of the Laplacian operator. So I just generalized this result. Now, the question is the following. Okay, we define this Pc, but is it really the critical exponent? So, according to the definition which I gave before, it is not always true, but it is true under sufficient conditions. So, in particular, assuming the initial data to be in L1 and the integral of f to be greater than 0, one can prove that if Pc is greater than 1, and the nonlinear problem with classical power nonlinearity, modulus of u to the power of p, admits a weak solution, a global weak solution, then for sure p is greater than Pc. So this means that for all p less or equal to pc, you don't have any global weak solution. So the non-existence part is proved independently on the operator L if you have this sign condition on the integral of f. On the other hand, if still pc is greater than 1 and there exists r greater equal 1, such that for all, assuming the initial data to be in L1 intersect Lr, one has that the solution to the linear problem is in LQ, and the LQ norm of the solution to the linear problem decays at least like 1 plus t to the power of minus 1 over pc, then one can prove that taking initial data to be sufficiently small, our nonlinear problem with power nonlinearities admits a global solution. So for all p greater than pc. So in practice, if the solution to the linear problem decays sufficiently fast, at least like 1 plus t to the power of minus 1 over pc, then there exists a solution to the nonlinear problem for all p greater than pc. Again, also this result is not so surprising, and in particular in the literature for different and several choices of L, it was already proved with also many details about, and more precise details about the linear estimates and the regularity of the solutions. But these two propositions allow us to understand some sufficient conditions under which the exponent pc, which we defined, is really the critical exponent. And under these conditions, we will be able to discuss and to give a critical condition also on the modulus of continuity. So just to understand better the application of this constructive method, we consider, for instance, this sigma evolution equation with structural damping. So in this case, what is the set capital J? The derivatives which are in the equation have order 0, 1, and 2. In particular, R0 is 2 sigma, R1 is 2 delta, and R2 is equal to 0. So this our function g of eta will be the minimum of 2 eta, eta plus 2 delta, and 2 sigma. Of course, now this minimum depends on the values assumed by delta and sigma. In particular, what one can see is not so explicit, but you can believe, is that pc is equal to 1 plus 2 sigma over the positive part of n minus 2 delta, if 2 delta is in 0 sigma, so we are in what is known as effective damped case. Instead, if 2 delta is greater than sigma, pc is equal to 1 plus 2 sigma over the positive part of n minus sigma. So this is pc, and so proposition 1 guarantees that for all p less or equal to pc, if the integral of f of the initial data is greater than 0, for sure this nonlinear problem with power nonlinearity assumes no global weak solution. On the other hand, from the literature, it is known that if we are in the effective case, so 2 delta in 0 sigma and n less than 2 sigma, then the solution to the linear problem satisfies these long time decay estimates for all q between 1 and infinity. Here you can see that this exponent in absolute value is increasing, so the decay becomes faster when q becomes larger. And in particular, what you have is that for all q greater equal to pc, if n is between 2 delta and 2 sigma, then the solution to the linear problem satisfies the desired linear estimates. So for all q between pc and infinity, the Q norm of the solution to the linear problem decays at least like 1 plus t to the power of minus 1 over pc. And so this means that we will be able also to apply proposition 2. We have something very similar in the case, in the non-effective case, so in the case 2 delta greater than sigma. if sigma is strictly greater than 1, and n is between sigma and 2 sigma. So in this case, the solution to the linear problem satisfies this long time decay estimate. And also in this case, what one can see is that if Q is greater or equal to PC, and here PC is the one which we found in the previous slide, then the solution to the linear problem, the Q norm of the solution, satisfies this linear estimate, so decays at least like 1 plus t to the power of minus 1 over PC. Okay, these linear estimates were obtained already in the literature in these two papers. And so, in both the cases, the application of proposition 2 allows to prove also the existence of global small data solutions for every p greater than PC. So we have both the existence and the non-existence part. So PC is, for this model, really the critical exponent. So now the idea, as I already told you, is to fix P equal to PC. Now we know, at least under these sufficient conditions, which is an expression for the critical exponent, and we multiply this power nonlinearity by a modulus of continuity. So what we can prove is that if the integral of the initial data is greater than 0, and the nonlinearity modulus of s to the power of PC times mu modulus of s is convex, this is just a technical assumption, then if the nonlinear problem with nonlinearity modulus of u to the power of PC times the modulus of continuity admits a global in time solution, then for sure the integral of mu s over s in the S is less than infinity. So we find the same necessary condition which we had for the classical damped equation. On the other hand, if, again, PC is greater than 1 and there exists R greater or equal 1, such that for all fixing the initial data in L1 intersect R, the solution to the linear problem, the Q norm of the solution to the linear problem decays at least like 1 plus t to the power of minus 1 over PC for all Q greater or equal to PC, so including also infinity. Then, if the modulus of continuity satisfies this integral condition, together to some other technical assumptions, we can be sure that assuming the initial data to be sufficiently small in L1 intersect LR, the nonlinear problem with the nonlinearity modulus of u to the power of PC times the modulus of continuity admits for sure a global in time small data solution. So we have, under these sufficient assumptions on the solution to the linear problem, and so this means on the linear differential operator L, we have also the existence result. So this is really a critical condition on mu, and it coincides with the critical condition which we had for the classical damped wave equation. So I want to at least sketch the proof of the non-existence result. The proof is based on a general test function method introduced for the first time in this paper by Ikeda and Sobashima in 2019. So first of all, okay, we notice that, again, I just recall this, that since PC is greater than 1, there exists eta bar between 0 and infinity, such that PC is exactly the value of our function age in eta bar. This eta bar will be important in the definition of the test functions. So now, again, we want to define these test functions. So we introduce these cutoff functions, key of S, which is a function which is 1 between 0 and 1 over 2, is 0 for S greater than 1, and it is decreasing between 1 over 2 and 1. And as usually, it is a C-infinity function on all the interval 0 plus infinity. And then we also introduce this auxiliary function key star S, which in practice coincides with key for S greater than 1 over 2, instead it is a 0 for S between 0 and 1 over 2, which is the role of this key star S. In practice, you can notice that if you make the first derivative of key, this is exactly equal to the first derivative of key star. So key star will be useful for us to underline that the derivatives of key as n whole close to 0, so have support included in 1/2, 1. Okay, so it's a notation that will be useful later. And then the idea is to define as a test function to which we will apply the definition of a weak solution, this psi of tx equal to key to the power of q, evaluated in t plus modulus of x to the power of eta bar. Here again, eta bar is the value of eta in which we have that pc is equal to age of eta bar, so in which that maximum is assumed. Okay, and similarly to before, we also define this function psi star. In particular, okay, for all r greater than 0, we can apply this scaling argument. So we define this psi r equal to psi of t r minus 1 x r to the power of minus 1 over eta bar. And similarly, you have the definition of psi star r. What you can notice is that the support of psi r is a subset of this set qr, which is the product of the integral of the interval 0r with the ball of radius r to the power of 1 over eta bar. Instead, psi star r has a hole around 0, which is proportional to r in practice. Okay, so the radius of this hole is proportional to r, and this will be very important later. So now, suppose by contradiction we have introduced the test function, and suppose now by contradiction that our nonlinear problem admits a global in time weak solution, even if the integral of mu s over s is infinite. So, since this global solution exists, we can define this integral term IR, where f is our nonlinearity, and then applying the definition of a weak solution and suitable estimates on the derivative of the test functions, we can get this inequality. So, this inequality is already important to understand the constructive method for the critical exponent. So for a moment, forget the modulus of continuity, suppose that we have f of s equal to modulus of s to the power of p, then writing explicitly what is f to the power of minus 1, we get here this inequality. So on the left-hand side, you have the integral of f times psi r, which is something which for sure is positive, at least for r sufficiently large. Instead, on the right-hand side, you have these powers of r times this integral term. What one can see is that one can get a contradiction every time that this exponent of r is less or equal to 0. One gets a contradiction taking r that tends to plus infinity. So I don't add other details, but fixing the exponent to be less or equal to 0 means exactly to ask that p is less or equal to pc. So you see, this pc now here is determined by scaling arguments. Now, let's go back to the nonlinearity which includes also the modulus of continuity. In this case, we need to refine our method, and so we, following the idea of Ikeda and Sobashima, we introduce this function, small y of r, which is the integral of the nonlinear term times psi star r. Psi star, I recall, has that support which has an hole around 0. And then we define capital Y of r equal to the integral of small y of r times r minus 1. Okay, it's quite technical definition. So what one can prove is that, what one can just notice is that for y...
Girardi,
Yes.
Just 1 second. No, just to remind you that you have 10 minutes more, okay? 10 minutes.
Okay. Thank you. So from the last estimate, we just, we know in practice that we can derive for this function capital Y of R, this last inequality, which is a differential inequality in practice. And so what a differential inequality in the variable Y of R. So the function is in inequality is Y of R. And writing more explicitly this inequality, what we get is that for all R greater than R0, we have that 1 over R times the modulus of continuity applied to constant over a certain power of R is less or equal to Y prime of R over Y of R to the power of PC. Okay? So now integrating with respect to R in practice, both the left-hand side and the right-hand side, one gets that this integral is less or equal to a finite quantity. This is a finite quantity since PC is greater than 1. So from this inequality, you understand that if the left-hand side is, which is the integral of mu over s is infinite, you get a contradiction when R tends to plus infinity. So our necessary condition on the integral of mu s over s comes exactly from this inequality. So this is the idea of the proof of the non-existence result. Okay, in the existence result, I will be faster, and the idea is to apply a Banach fixed point argument. So we fix a space for the solution, which is this space X, in which we want to prove the existence of a solution, and we endow this X with a certain norm, which is the supremum of 1 plus S to the power of 1 over PC, times the norm of US in LPC intersect L infinity. This definition of norm is related to the estimates which we obtained for the linear problem. And so now what one can notice applying Duhamel principle is that U is a solution to our nonlinear problem if and only if it satisfies this identity. So it is equal to the solution to the linear problem plus this integral operator n applied to U. The argument of this integral is in practice the solution to the linear problem with initial time s and the second and initial data f of U of s. So this is a common method. And so this means that U is a solution in practice if and only if U is a fixed point for this operator G. So in the remaining part of the proof, the idea is to prove that G is well defined, so is really defined from X with values in X, and moreover, it is a contraction. And one can see that this is a direct consequence of these two estimates. So it's immediate to see that since the solution to the linear problem satisfies that sufficient conditions, for sure it belongs to the space X and satisfies these estimates. And also, after some calculations, one can also prove that the norm in X of nu minus nv satisfies these estimates. This second estimate allows to conclude both that for all u, nu is in X, and moreover that n is, and then g is a contraction. So, I will omit the details, but what is important is that in order to prove the last estimate, so in order to estimate the LQ norm of nu minus nv, at some point you need to guarantee that this integral of 1 plus s to the power of minus 1 times the modulus of continuity is uniformly bounded with respect to t. And so from this, you get the necessary, the sufficient condition, sufficient condition on the integral of mu s over s. Okay, so and then applying again a contraction argument, you can get the desired result. So again, let us give some examples in which you can apply this result. If you again consider the sigma evolution equation with structural damping, we evaluated already PC, and since we are exactly in the case in which sufficient conditions are satisfied, we can say that if the integral of the initial data is greater than 0, a global small data solution exists if and only if mu satisfies this integral condition. So the same which we found for the classical damped wave equation. This result applies also to several different higher order differential operators, the higher order dissipative evolution models in particular. As an example, you can consider the following, which is related to a coupled system of elastic waves with some Maxwell equations in space dimension n equal 3. So this is a differential operator of order 5 with respect to t. And what one can see is that applying our constructive method, one obtain PC equal to 5. And in particular, it is known from the literature that the solution to the linear problem, to the corresponding linear problem, satisfies this estimate. So the LQ norm, for every Q greater or equal to 5, the LQ norm of the solution to the linear problem decays at least like 1 plus t to the power of minus 1 over 5. So we have all the sufficient conditions to apply both our main results. So the corresponding Cauchy problem with nonlinearity modulus of u to the power of 5 times the modulus of continuity admits a global in time small data solution if and only if it satisfies this integral condition. Now, again, which is a natural question. A natural question is this condition then independent on the choice of L? The answer seems to be not. For instance, if in the case in which the equation includes a zero-order term, and then PC is equal to 1, one can prove the following result. So one can prove that if the solution to the linear problem decays in the LQ norm at least like 1 plus t to the power of minus beta for all q greater than a certain delta, which is the space in which you take the data, then you can prove whatever is the modulus of continuity which you consider, that the corresponding nonlinear problem with nonlinearity modulus of u times mu of modulus of u admits always a global in time small data solution. So whatever is the modulus of continuity without any additional integral assumptions on mu. So you always have global existence if, again, the solution to the linear problem decays like at least like 1 plus t to the power of minus beta with beta strictly greater than 1. Okay, I will avoid the proof. And as an example, what one can consider a sigma evolution model with the damping and mass. So in this case, what we know is that if sigma is greater than n over 2, the solution to the linear problem in the RQ norm decays exponentially. And so in particular, our sufficient condition is true for all beta greater than 1 arbitrarily large. And then what one gets is that this problem with nonlinearity modulus of u times the modulus of continuity applied to modulus of u admits a global in time small data solutions, whatever is the modulus of continuity which you consider. On the other hand, if we consider the classical nonlinear wave equation with so without any damping, what we know is that the critical exponent is not determined by a scaling argument, and it is the the famous Strauss exponent. So this problem was already studied by Chen and Reisig in a paper on a mathematician Allen, and they proved that in the special case in which the modulus of continuity is, at least for small u, equal to minus the logarithmic of u to the power of minus alpha, you have the existence of global small data solutions if and only if alpha is greater than 1 over the Strauss exponent. So in this case, you don't find the existence for all alpha greater than 1, but so alpha equal 1 is not a critical value in this case, but the critical value becomes 1 over the Strauss exponent. So you have a different critical condition. So it is interesting for us to understand, still an open problem, to understand how really this critical condition can depend on the operator L. So again, these are the references for this talk, and thank you for your attention.
Okay, thank you very much, Professor Giovanni Girardi, for your very nice talk.
Thank you.
Very clear talk. Okay, so we are open for questions. Does anyone have a question for Professor Girardi? Maybe you can raise your hand, then we can unmute your mic.
Sorry, may I have one?
Yes, please.
Oh, sorry. This is a question from Midnight Japan.
Yes.
Your broad result, you always assume that the moment of the initial
Yes.
speed is strictly positive.
Yes.
Well, what will happen if it's 0?
Okay. The point. Do you see my screen still? Right. Yes. Can you see my screen?
Yeah, of course.
Okay. Perfect. Okay. The point is that if okay, the main point is in this remark. Okay. So if you have that the integral of f is 0, then when r tends to plus infinity, you are not really able to get a contradiction. You need to have this positive quantity on the left-hand side in order to have the contradiction. Yeah.
But if you're working on the to measure the lifespan estimate, then it's almost a one-sided condition. If it should be 0, then you will get a better lifespan estimate, right?
You mean if the momentum is 0, you can get better lifespan estimates?
Yeah, of course.
Honestly, I don't know. I still didn't discuss lifespan estimates for this problem. For us, it's typically to assume that yes, that the momentum is greater than 0, and yes. Okay, if you discuss lifespan estimate, this means you don't take r that tends to plus infinity. You discuss the larger value of r, let's say, that you can take. So it's a bit a different argument. Here, the contradiction comes when you take r that tends to plus infinity. So it's yes. So maybe about in the lifespan estimate, maybe you can still do something. Yeah, I think so.
Oh, okay. Thank you. Let's discuss in somewhere else.
Yeah, sure.
Okay.
Thank you.
My name is Takamura.
Okay.
Sorry. I cannot.
We already met in Bari sometime. Yeah.
I cannot modify my name. This is written in Japanese language, I think. Sorry.
Thank you.
So I have no question, but I want to thank Giovanni to his very nice talk. And also I want to ask you to pass greetings to Reisig from Tbilisi, from Manjavidze family.
Yes.
If it's possible. Yeah.
Sure.
Thank you.
Yes, I hope to meet him soon. So yes.
Okay. Okay, great.
Okay, thank you very much. So I have maybe some questions for Professor Giovanni Girardi, but I prefer maybe to email him.
Yes, perfect.
Maybe
Thank you.
because our technical questions, I don't want to disturb
Yes.
you.
Thank you.
I will email you later. So, okay, it's very nice to see the interest of our audience in our talks. So probably we are going to start then in 1 hour with the talk of Professor Nino, right?
I'm here. Yeah.
That is here. So, okay, so let's see the time. So at 18 in Central European time, we are going to start, right, with your talk.
So it will be so 9 hours. So not 9 but 10. Yes. Sorry. After 2 hours. Yeah.
At 6 p.m. 6 p.m. in Central European time. In 1 hour. In 1 hour.
So 6. Okay.
6 p.m.
6. It means for us. I need to add 4 hours. So it means 10.
Right for you. Thank you. I'm sorry for the.
Yeah.
You're doing a big effort, right, to joining us.
Okay.
Yes, thank you very much.
So see you soon.
See you soon. Okay. Alexandra. Muchas gracias, Alexandra. Entonces, regresamos en 1 hora y mientras tanto vamos a compartir nosotros aquí. Muy bien, entonces vamos a compartir aquí. Sí, por algún momento. No, por algún momento no, por alguna razón no he podido activarlo. Sí. A la hora de compartir. Listo. Listo. Ok, lo voy a dejar así por el momento. Muchas gracias, Alexandra.
ICMAM Conference on Analysis in Developing Countries. We remind our attendees that there are still 3 talks coming up before finishing our schedule today, each followed by a question and answer session. So please feel free to drop your questions or remarks either in this chat or on YouTube.
So it will be after the lectures. It will be after lectures, yes?
3 lectures, including yours.
2, yes, but questions?
At the end of the talk, exactly.
Oh, I see.
Yes. And okay, so it's my pleasure to introduce our next speaker, Professor Nino Mangiavice from Ilia State University. She's going to share with us some insights on functional properties of the solutions of some classes of 2-dimensional elliptic systems. So Professor Mangiavice, on behalf of the organizing committee, thank you very much for accepting our invitation. And the floor is yours.
Yes, but thank you to you. Thanks you for giving me the chance to participate in such honorable event. Tribute to Professor Luigi. So, Rodino, I am a life member of ISAC, so I know him. We are so this is joint work, as you can see, with Professors Giorgadze and Macazzaria. They are working in we are working in different universities, but so we are members of one complex analysis group, which is at Ilia Vecua Institute of Applied Mathematics at Tbilisi State University. This department was founded by Ilia Vecua. So then chair was Professor Mangiavice. Now chair is Giorgadze, Professor Giorgadze. So now I will see only my presentation. Okay. So our talk consists of 3 sections. The first is in which the functional properties of the theory of generalized analytic functions and the theory of vector functions are presented. The second section consists of the modulus principle for generalized analytic vector functions, and it is shown that maximum modulus principle can be formulated basically as in the classical case, and thus the problem posed by Professor Boyarsky is partially solved. As for the second section, the generalized analytic functions with singular coefficient and for them, in some sense, complete analysis of the boundary value problems of the theory of functions are given. So this work was supported actually from the Shota Rustaveli National Science Foundation. So this is our first section, which is called on the structure of regular generalized analytic functions. So as in this section, so-called Kaleman-Berzweg equations of the complex plane are considered. Such kind of equations, the study, intensive study of such equations began in the middle of the last century. You can see very, very famous monograph of Ilia Vecua, Generalized Analytic Functions, and has not lost its relevance to this day, since the solution of several important theoretical and practical problems is directly reduced to such equations. In this direction, the most principal and profound results have been obtained by various authors, but a number of interesting problems remain open, and the solution of which is important not only from theoretical point of view, but for practical reasons as well. We have introduced special classes of solutions of the mentioned equations, which we call generalized meromorphic functions. And we study them both from the point of view of the pure theory of functions, as well as from the point of view of the analysis of boundary value problems of the theory of functions. Sufficiently important information about the behavior and therefore the structure of the generalized meromorphic functions in the neighborhood of the point of infinity has will be determined. Below everywhere we will use the following notations. C denotes a complex plane of the variable z. The number p is greater than 2. The regular coefficients a and b belong to the class LP 2c. This is so they are regular, it means, but this class was introduced by Iliaveco by the special purpose, because of why I want to provide its definition, because to be exact, to have just exact definition of this class. So what do we mean under F belongs to LP2? It means that if the following two integrals are finite on a unit circle, then we say that function belongs to this class. So we define this class according to Iliaveco. The generalized analytic functions are the solutions of the equation 1, 1. You can see this equation, and they are called Karleman-Berswegwe equation in nowadays. So, and derivative here is understood in Sobolev sense. So general representation of the generalized analytic functions by means of the analytic functions is the strongest tool to investigate the solutions of this equation. So in particular, there exists such formula. So WZ is solution of the Karleman-Berswegwe equation, phi z is analytic function. And you can see that it is analytic function times e in power omega z. This is formula 1, 2. And by this formula, the bijective relationship between the generalized analytic function and classical analytic functions is established. Phi is called analytic divisor of analytic function W. And you can see omega here, omega z, formula 1, 3. You know that it's very essential, because of why I'm talking about it, that the general solution is given by means of an analytic function having then times e in power having the degree, the function omega z. And at first you may think that this representation seems to automatically transfer the properties of the analytic functions to the solution, but can you see that omega z is participates itself in representation of omega z, so it is not so easy. So in some cases it is really easy to transfer properties of the function phi, but sometimes you can imagine that we can run into the problems that are still unsolvable. So this, I am speaking about this A and B. these coefficients are regular, then many properties pass throughout any difficulties. But in case of the singular coefficients, we manage to get some results, but this is a matter of another talk, and we will not touch it here. So every bounded solution of the equation, Karaman-Bersui-Vecqua equation, with regular coefficients have exactly the same property as the entire function of the complex variable. Now consider the following system of the first order differential equations of complex variable, which is essential and central object of the research of the theory of ordinary differential equations. You can see this equation. So here the coefficients are given by the formula 1, 4. N is a natural number. So here A, K, P are the complex numbers. Rho Z is given by formula 1, 5, and so M and nu are M is integer, but nu is just a real number. Omega K, Z are unknown functions, and we can rewrite it in the matrix form 1, 6. And everywhere below, we assume that it's not. The determinant is not equal to 0. It's non-singular, and eigenvalues and the numerical parameters m and nu satisfy the conditions 1, 8. So these conditions, like so you can see it, formula 1, 8. So for this system, we have proved the analogues of Liouville type theorems, and firstly, before I tell you about theorems, I want to show you what it means, what we mean under the class omega n delta sigma. So denote by omega n delta sigma the set of all vector functions omega z representing the solutions of this system. This is matrix solution, matrix system, and satisfying the asymptotic conditions. You can see it 1, 10. Here n is non-negative integer, and delta and sigma are non-negative real numbers. For any integer, non-negative integer n, theorem 1, dimension of this space is 0. Theorem 2, dimension of this space is 0 as well. If here you can see the conditions. Here, theorem 3, dimension of this space is infinity. When sigma is greater than tau, tau is connected with eigenvalues of the matrix. Here you can see theorem 4 and 5. Theorem 4 and 5, these theorems are analogues of classical Liouville type theorem. So I skip proof of these theorems, just only just theorems. Now I want to introduce what we mean under the function generalized meromorphic function. Let D belongs to C. C is a complex space. Be a discrete set D, such kind of set in infinite. W is called the generalized meromorphic function with D singularities if these two conditions are fulfilled. W is a generalized regular solution of the equation, Karl-Lemon-Berswek equation. Omega Z approaches infinity when Z is approaching to Z sub K. And I want to recall once more that the research of generalized analytic functions is based on Weck-Wass theorem, and this representation where omega is given by special formula, these formulas they hold. Now I want to so we call, and it is really conventionally just a problem. Just we call it problem A because of its essential importance. Given a number nu from R positive, a continuous function upper H with the period 2 pi and non-negative entire number n, you can see it. And the problem is find a generalized analytic function W such that it satisfies this asymptotic condition 112. 112. Probably it's well known what is L plus. So now we have additional theorem, theorem 6, because we had 5 Liouville type analogs of Liouville type theorems. Now let upper H be a function such that if there exist the numbers phi 0 from R and n from n, so integer, for which there are conditions, such kind of conditions fulfilled, where pi k is pi 0 plus 2 pi k over n, and nu is less than n over 2, it turns out that the solution of the problem A in the class of generalized meromorphic functions, WZ is generalized rational function whose order of pole at infinity does not exceed n. Therefore, the function phi in this representation will turn out to be a rational function whose pole order at infinity does not exceed n. Now I want to make some remarks. If nu is 0, h is arbitrary function, just any function, n is 0, and the coefficients a and b are zeros almost everywhere, then theorem 6 gives us Liouville classical theorem. Remark 2, as was mentioned above, so problem A has many applications in this investigation of the Karl-Lemon-Berswek equation with the singular coefficients, not regular but singular, but it's another subject and we will not touch it here. One more remark. Theorem 6 allows us to pose correctly the boundary value problems for the equation, Karl-Lemon-Berswek equation, and to make, in some sense, their complete investigation. These were the remarks I want to make. So, to tell you, and also, I want to, so this is theorem 7. If the generalized analytic function omega z satisfies 112 this asymptotic condition, then and upper age satisfies such inequality, then omega z is just trivial function. And I want also to note that this part of our talk can be considered as a continuation of our work. We have published monograph, so this whole our complex analysis group in 2012, elliptic systems on Riemann surfaces, and this is actually continuation of this work. So now we start part 2, maximum modulus principle. You know that one of the major problems of complex analysis is the investigation of analytical holomorphic functions, or in other words, the investigation of some specific relation between the dependent variable W and independent variable Z. And so here are various concepts, but the Riemannian concepts is distinguished among them. And you can see here very well-known Cauchy-Riemann equations, 2-1. This system is simply a elliptic system of first-order partial differential equations. The idea of investigation of the properties of objects, functions or systems of functions, by means of the information that they satisfy some differential equations, system of equations, is the starting point of many theories of mathematical analysis. For example, such as analytic theory of differential equations, which is actually very actual sub direction of complex analysis. I will skip some things here. The main thing is just part which is connected with the problem of Boyarsky's problem. The main result of the second section is the solution of the Boyarsky's problem. He is one of the most prominent followers of academician Ilya Vekua, and the author of fundamental results of the theory of generalized analytic functions and the vector functions. In the survey paper, his paper is called Generalized Analytic Vector Functions. Several interesting problems are started. One of them will be discussed below. So, below, G denotes the domain of two real variables, x and y, in R2, and gamma is its boundary. Consider the following two matrix functions, A and B, where n is arbitrary natural number. The components of this matrix function are arbitrarily functions defined in G. By means of these matrix functions, A and B, the system of first-order partial differential equations is defined. This is 2-9 formula, which plays an important role in the study of theoretical and practical problems of contemporary mathematical analysis. So this system satisfies condition of ellipticity. You can see it, this condition. So we can rewrite this system in the vector form, 2-11, and all systems 2-1 or before we are speaking, all these systems are partial cases of this system, 2-9. So, one of the fundamental results of the classical theory of complex function is the maximum modulus principle, which has many important applications, not only in the theory of functions. In turn, this principle is the basis of the further in-depth studies. And in this talk, we deal with the analogs of this classical principle, namely the validity of this principle for the elliptic system. Elliptic system 210 will be investigated, that its analog will be obtained. So I will skip now this part as well, and I will speak just about Boyarsky's problem. In his very famous paper, Boyarsky noted that the maximum modulus principle is in a weak form is valid for the equation. This is Karl-Member's equation in complex form, and points out that there is no answer to the following interesting question: is the same valid for the elliptic system 211? So this is the system 2-9 in a vector form. So to state the corresponding result, it is convenient to write this system in a well-known complex form. Due to the elliptic condition, the natural number n is necessarily even, so n is to n, upper n is to n, assumes that the coefficients of the elliptic systems are such that after reducing the system to a complex form, we obtain the system of complex equations with respect to the complex vector function W, you can see it, where C, K, P are complex, gamma is continuous in gamma bar, and anti-holomorphic in gamma. The following theorem holds: let C be a matrix with complex components satisfying the condition commutativity 220, where if C is this matrix, then C star is its Lagrangian conjugate. Then for every solution of this system, which extends continuously in G, the following inequality is valid: 221, where Z0 is an arbitrary point in G bar, omega W is given here, is given by this formula. So it is what's the square root from this presentation. Moreover, if for at least one point Z0 from G in 221, the inequality holds, then they are all constants. They are all constants. The condition 220, this condition, so this is commutativity, is essential for this theorem. And is the sufficient condition for Boyarsky's problem? Okay, then it's better to, or actually here you can see finally an example of a concrete system for which all the conditions of the theorem are fulfilled. Now I want to start the second part. Probably I have time, yes. The boundary value problems for the first order elliptic systems on a complex plane were investigated extensively over the past years. Yes, the first order system of partial differential equations, you can see it where u is given is 2n desired vector, a and b are given real 2n matrices depending on two variables x and y. Upper f is given 2n vector. This system is elliptic in some plane domain D if and only if the matrix has no real characteristic numbers in D. When n is 1, in case of sufficient smoothness of the coefficients of this system, after corresponding change of variables, this system can be reduced to one complex equation. So here you can see that what do we mean under dz bar. So, and this is system called also Karleman-Bersel equation, but it is not non-homogeneous. Consider the Riemann-Hilbert boundary problem for the following Karleman-Bersel equation with the polar singularities in the domain G. G is a finite m+1 connected domain of the complex plane Z with sufficiently smooth boundary, provided that the given functions lambda and gamma are the Hölder continuous function. It is well known that the equation, Karleman-Bersel equation, in case of regular coefficients, the condition lambda is not equal to 0, lambda t is not equal to 0, t belongs to gamma, provides the neutrality of the problem of the Riemann-Hilbert problem in the class of continuous in G bar minus Z0 functions satisfying the equation CBV in G minus Z0 and the asymptotic conditions hold. Here Z0 is some point in the domain G and sigma is some real number. For the Karleman-Bersel equation with the polar singularities, the situation is essentially different. It is known that there exists sufficiently wide class of equations permitting only trivial solutions in the domain G minus Z0 and satisfying the asymptotic condition where Z0 is the point of polar singularity of the equation, Karleman-Bersel equation, sigma is a real number. Therefore, it makes no sense to consider the boundary value problems in this class. On the other hand, if there are no restrictions on the solutions of the in the neighborhood of the singular point Z0, then it may occur that the homogeneous boundary problem has infinite number of linearly independent solutions. So maybe so in the first part, so this section consists of two parts. In the first part, the above mentioned asymptotic conditions are obtained, and the general representation of the solutions of the Karleman-Bersel equation with the polar singularities satisfying these conditions are constructed. So this is part one, the Karleman-Bersel equation with the polar singularities. So now I want to tell you, just omit these things, and I think that most important is to tell you about part two, investigation of the Riemann-Hilbert boundary value problem and the main theorems we have obtained. probably I have time. So to pose correctly the Riemann-Hilbert boundary value problem, it is clear from the above mentioned, but above results that it is sufficient to require from the solution of the equation, Cardinal-Berswag equation, the fulfillment of the asymptotic condition like this equation, star. You can see this equation. In this part of the present section, the proof of sufficiency of asymptotic condition, this equation with star is given, and boundary value problems are investigated. So let's I think I can so we can consider this boundary value problem here because I have probably enough time. So on the boundary gamma, the Hölder continuous functions lambda t and gamma t are given. Gamma t is a real function, and the absolute modulus of lambda t is 1. Find the function omega z from the class omega 0 delta sigma bar, satisfying the boundary equation real part of lambda t times wt, lambda t bar times wt is equal to gamma t. T belongs to the boundary. And here we have very interesting theorems. We have obtained very interesting theorems. The homogeneous boundary value problem. So 314. So you know this problem, Riemann-Hilbert problem. In this class has infinite number of linearly independent solutions if and only if one from the following conditions is fulfilled. Here you can see two conditions. I will omit this proof here. And yes, then based on above results, this following theorem becomes evident. The homogeneous problem 314 in the class, but here it's different. Here you can see stars, so has finite number of linearly independent solutions, and the homogeneous problem is solvable if and only if this condition is fulfilled. One more. Let L be a number of linearly independent solutions of the homogeneous problem of this of 314 by means of the following evident inequality. You can see here it follows the validity of the next theorem. The following condition. So this is just index, so L minus L star is equal to 2n plus 2 times sigma, 2 times real part of Q, k minus m plus 1 take place, where Qk is a residue of the function Qz at the point zk, From the results, from these above results, in particular, we get this theorem that for the problem 314 to be Noetherian in the class gamma 0 bar delta sigma, it is necessary and sufficient the fulfillment of the conditions. Here you can see conditions. I think it's already 14 minutes. So here you can see the references we used here. And so thank you for your patience. So thank you for your patience, and thanks to organizers once more.
Thank you very much, Professor Mangiavice, for this comprehensive talk. So I would like to address our audience. Are there questions maybe for Professor Mangiavice?
You can send me your questions if you want, so I can mail you answers if you want.
Maybe I can start. Not really sure whether I missed this part. Can you go back, please, to condition 1.12 on problem A, I think?
Problem A.
Problem A, correct. Yes.
I will. So now, okay. Just problem A. It is on page.
I think it's page 7.
7. Let's take one. Yeah. Yeah.
Great.
Yeah.
So exactly. So I'm talking about this condition. So in the second part of your talk, you were essentially studying some applications to elliptic complex systems, if I understood correctly. So I was wondering whether this condition is this condition the same for this setting, or it somehow changes?
Yes, this condition is the same. Yeah.
Is it the same?
Yeah. Yeah.
Okay. All right.
Yes. So this means that so it is when it is this is just greater than 1, then it is just a normal logarithm.
Exactly.
Yes.
Okay. So yes. Are there further questions, maybe? Okay, apparently that's not the case. So thank our speaker once again. Thank you very much.
Thank you. And please welcome to Georgia.
Absolutely. Thank you.
Yes. We have also very interesting conferences. And please participate. So I will send an invitation. So.
Looking forward for it. Thank you.
Okay.
Okay, so we start in 70 minutes maybe with our next talk. So see you in
7
minutes. Exactly. Thank you.
So see you then.
See you. Bye.
Bye.
Alexandra, me disculpas, olvidé decirte. Okay, thank you very much. We resume our conference with yet another interesting talk, this time by Professor Jenny Fragnelli from the University of Siena. She's going to discuss Carleman estimates and null controllability for non-autonomous degenerate parabolic problems. So thank you very much for contributing to this conference, and please.
Okay, so thank you very much to the organizers, in particular to Duvan for this kind invitation. For me, it's a pleasure to be here and to give this talk. In my talk, I present some new results on non-autonomous degenerate parabolic problems. In particular, I will focus on null controllability and Carleman estimates. And these results are obtained in collaboration with Mohammad Akil from the University of Valenciennes and Sarah Ismail, who is a PhD student of mine from the University of Bari in Puglia, in Italy. The motivation to study this problem is the well-known Boudico-Seller model. It is known that in 1968 and in 1969, Boudico and Seller introduced independently an energy balance model that can be rewritten as in the one-dimensional case as an equation of this type, where U is the surface temperature at time t and position x. X is the space variable and belongs to -1, 1, where -1 is the south pole and 1 is the north pole. Rho zero is a positive constant. The function A is given by 1 minus x squared, so A degenerates is 0 at -1 and 1. The quantity Re and Ra are defined in the following way. So Re is the energy emitted by the Earth in the Boudico cell, in the Boudico model is given by this function. In the Celler model is given by the Stefan-Boltzmann law, given in this way. Here, the function epsilon is the emissivity, and it is a regular positive and bounded function. The quantity Ra is the fraction of the solar energy absorbed by the Earth. It is given by the product of two quantities, Q and beta. Q is a function that depends on T and on X, is the incoming solar radiation flux. In time scale, when the time scale is smaller, for example, in seasonal models, one can assume that Q is a time periodic function. If the time scale is long enough, for example, in annual models, then Q can be considered independent of time. Beta is it depends on U, on the temperature, and is the co-albedo. It is given by 1 minus the albedo alpha U. The albedo is a very important concept in climatology. It represents the fraction of light reflected by a surface. In general, it belongs to the interval 0-1. Clearly, albedo is a property that every object has, like a car, mountains, snow, and the earth as a whole. Comparing the albedo of different color cars, we have that clearly the white car reflects more of the sun energy with respect to the black cars. So the white cars has a higher albedo with respect to the black car. Indeed, in the summer, black cars are hotter than the clear ones. Several factors can influence the albedo of a surface. Surface composition, soil moisture, surface texture, vegetation, land use, and the angle of incidence. For example, rough surfaces has a lower albedo with respect to smooth surfaces. Ice, snow, sand have high albedo with respect to forests, oceans, asphalt. For example, dark asphalt and dark rooftops in urban areas can absorb up to 90% of incoming sunlight. Also, the angle of incidence is very important. For example, lower angles, so in the morning and evening, result in higher albedo with respect to right angles, so in the middle day. And just to summarize, surface with the snow and ice reflects more heat with respect to surface without snow and ice that absorb more heat. So when it is getting colder, ice cover expands and albedo increases. And due to the importance of this Boudico-Celler model, this model was studied from a lot of people and from different points of view. For example, here there is just a list of a few papers, but there are a lot of other papers. I just want to recall these few papers. In the paper of Badi, the author studies the existence of a periodic solution Recently, Cannarsa, Lucarini, Martinez, Urbani, Van Costenoble study a two-layer energy balance model that permits vertical exchanges between a surface layer and the atmosphere. In particular, they study the dependence of the equilibrium points with respect to the involved parameters. And they prove that the surface temperature increases monotonically with respect to a parameter that denotes the absorptivity of the atmosphere. Then Cannarsa, Amalfitano, and Martinez study also a model with a memory term. They study existence, uniqueness, regularity, and stability. There is also a recent paper of Floridia where he studied controllability. I'll come back on this paper later, and I'll come back also on the paper of Esser later. I just say that he studied a non-autonomous model. Then there is another paper of Jie Wang, where they consider a model with Mashi region, and in their model, the constant ρ0 is a function that depends on x. And then I just recall this other paper of Thornton Van Costenoble, where they consider an inverse problem. So, in particular, we are interested in studying global null controllability for the problem. In particular, so we want to find conditions such that, as you know, there exists a function f, so that the solution at time t is 0 on the whole domain. In this case, the control acts in the interior of the space domain. And this omega is called the control region, which is in this case compactly contained in 0, 1. So global null controllability for the autonomous case is a well-known result. There are a lot of papers where the function is regular or also not too regular. But I'd like to recall that it is important that the space domain is bounded. In this case, I call the space domain omega. So for the Boudico-Seller model, omega is -1, 1. And it is important that omega is bounded since in 2001, Miku and Zozua consider an unbounded domain with a control region omega bounded. And they proved that the global null controllability fails in this case since an unbounded region is left without control. There are some positive results also in this case. For example, when omega is unbounded, the control region small omega is big enough so that the uncontrolled part is bounded. And another positive results can be found in this paper, where omega is 0 plus infinity, but and the control region is the union of these disjoint intervals that satisfies this condition. But as we have seen, there are a lot of applications where the function A is degenerate. For example, the Boudico-Seller model in climatology, but there are a lot of other applications. For example, in genetics, there is the Ruther-Fischel model where the space domain is 0, 1. The function is the product, the function A is the product of these two powers. So A in this case degenerates at 0 and at 1. Then there is in physics the model of Grushin, where the function A degenerates in the interior of the domain. In this case, the degeneracy points are in the interior of the domain, but outside the control region, which is this one. And another example is in biology, where the diffusion of small mammal species like rats can be described by an equation of this type. In this case, the function A degenerates due to the environment heterogeneity or barriers. And these mammal species are often found in conflict with the human interests. For example, it is enough to think to what happened in Australia 3 years ago, when there was an invasion of these rats. So it is really important to control the diffusion of, in this case, of these rats. But for the autonomous case, when A degenerates somewhere or in the interior or at the boundary, also in this case there are a lot of results. I just to recall that the first result is negative in the sense that if we consider the power with exponent greater or equal than 2, then global null controllability fails. Since using a change of variables, one can rewrite the equation as a neat equation on an unbounded domain. So we apply the previous results of Mikko and Svassula, according to which global null controllability fails. So it is important to obtain global null controllability. It is important that, for example, for the power, the exponent is strictly less than 2. But if the exponent is greater or equal than 2, then the only results that we can obtain is a regional null controllability results, in the sense that we can control the solution not on the whole domain, on the whole space domain, but only far away from the degeneracy point. In this case, we are assuming that the degeneracy point is 0. Clearly, this regional null controllability is a weaker property with respect to the global null controllability, since if global null controllability holds and if we stop to control the solution at time t, capital T, then the solution is still equal to 0 for time t greater than capital T. If regional null controllability holds, this is not true, due to the fact that on this part, the solution is not 0. But we can also, in this case, to prove that the solution is 0 for time greater than capital T. And but in all the previous paper, the problem is autonomous in the sense that the operator that we consider are independent of T. They are or in non-divergence form or in divergence form, but always independent of T. Edzer, in 1997, considers a very particular climate model, which is non-autonomous. In particular, he considers this equation. So if we divide by C, this equation can be rewritten as an equation of this type. So as you can see here, this function depends not only on x, but also on t. So it is non-autonomous. And for this reason, we consider a non-autonomous degenerate problem. So here the operator that we consider are the following ones. So we have the same operator as before, but we multiplied this operator by rho 0t. So the models, this model describes changes due to the season, for example. And clearly, due to the definition of this operator, we have that the domain of this operator are equal to the domain of the autonomous operator. Then on rho 0, we assume that is a W1 infinity function, strictly positive. This is important. We assume that the function A degenerates at the boundary, so at 0 or at 1, we are considering 0, 1, but we can consider a general bounded interval of R. Then we consider at the non-degeneracy point a Dirichlet condition. At the degeneracy point, we consider a boundary condition that depends on the operators, as we will see. On the degeneracy function A, we consider a weakly degenerate function or a strongly degenerate function. According to this definition. So if A is weakly degenerate, then A has this regularity. It is strictly positive in 0, 1, except for the degeneracy point where it is 0. And there exists a constant that satisfies this condition. So this constant belongs to the interval 0, 1 if A is weakly degenerate. If A is strongly degenerate, this constant belongs to the interval 1, 2. In the strongly degenerate case, we have also more regularity on the function A. So for example, we can consider the power x to k. If k is less than 1, we have the weakly degenerate case. Otherwise, if k belongs to 1, 2, then we have the strongly degenerate case. So about the boundary condition, as I told you before, on the degeneracy point, we consider always the Dirichlet boundary condition. At the degeneracy point, if we consider the non-divergence case, then we consider the Dirichlet boundary condition. In the divergence form, and if A is weakly degenerate, we have a Dirichlet condition. If A is strongly degenerate, then we have this Neumann boundary condition. And clearly, before studying the controllability, we have to study the well-posedness of the problem. In the non-divergence case, the natural Hilbert space where we work are the following spaces: L2 with the weight 1 over A, H1 1 over A, which is the intersection of the previous space with the usual H1 0, and H2 1 over A, which is the set of the function that belongs to H1 1 over A, such that the operator belongs to L2 1 over A. These are exactly the same spaces that we consider for the autonomous case, for the operator in non-divergence case and autonomous, in the paper in collaboration with the Cannarsa and Rocchetti. And in these papers, we prove that the operator in non-divergence form with this domain is densely defined and generates a contraction semigroup. For the divergence case, we consider the same space that we have in the paper in collaboration with Alabo and Cannarsa, where we consider the operator in divergence form always autonomous, an autonomous operator. So here there is a difference between the weakly degenerate case and the strongly degenerate case for the space H1A. So in the weakly degenerate case, we have the Dirichlet boundary condition. In this case, in the strongly degenerate case, we have the Dirichlet condition only at the non-degeneracy point. And now, thanks to the fact that the operator A1 and A2 generate a contraction semigroup and are densely defined, we can prove the following existence theorem for the non-autonomous problem. So we have that the solution is more regular if the initial data is more regular. Otherwise, if U0 belongs to L2, L2 with the weight or L2, then it is less regular. The idea to prove this existence theorem is to use the Kato theorem. So we have to verify that all the assumptions of this Kato theorem are satisfied. In particular, we have to prove that the domain of the non-autonomous operator are independent of T. And this is satisfied thanks to the definition of the operator. I recall you that the operator in the non-autonomous operator are given by the autonomous operator times the function rho 0 t. So they are independent on T. Moreover, thanks to the previous results, we know that these domains are dense in L2 with the weight or L2. Thanks to the assumption on the function rho 0, we can prove this estimate that it is important for the Kato theorem. And the last condition to apply the Kato theorem is to prove the following condition. So we have to prove that the operator every operator generates a strongly continuous semigroup, and the family is a stable family of strongly continuous semigroup. In the following sense, so it is enough to prove this estimate. And to do this, the idea is to introduce a new norm on L2 or L2 with the weight and on H1 1 over A or H1A that takes into account the term rho 0 t. In particular, we consider the following inner product. This inner product induces the following norm, which is equivalent to the norm on L2 or on L2 1 over A, thanks to the fact that rho 0 is a continuous function, and so on 0 capital T, so rho 0 has a minimum and a maximum. And so we can prove this equivalence. Moreover, we introduce these two norms on H1 1 over A and H1A, and again we can prove that these two norms are equivalent to the classical norm on H1 1 over A and H1A. And so, using this equivalence, we can prove that the estimates of the Kato theorem holds, and so we can apply the Kato theorem, obtaining the existence result. Now we consider the global null controllability. And as for the autonomous case, one can prove that the global null controllability is equivalent to the observability inequality for the homogeneous adjoint problem, which is given by this system. So here we have the same boundary condition that we have for the original problem. For the observability inequality, we have this one in the non-divergence form and the second one for the divergence form. Observability inequality, since we can estimate the integral on 0, 1 of v at time 0 with the integral of v at time t, where t belongs to 0 capital T, but here the variable x belongs to the control region, not on the whole domain 0, 1. And the idea to prove this observability inequality is to use some particular estimates called Karleman estimates. To do this, we have to add additional assumption on the function. In particular, for the non-divergence case, we have the following two conditions, which are the same that we have in the papers in collaboration with Cannarsa and Rocchetti, but in that papers, the function A is more regular, is C3. In this case, is C1. Okay. In the divergence case, we consider the following condition if the degeneracy point is 0, and this other condition if the degeneracy point is 1. I underline only that in the paper with Alabo and Cannarsa, we consider only the case when the degeneracy point is 0. Okay, so we have only this condition. In this case, we consider also these other cases. And as I told you before, so to prove the observability inequality, the idea is to use Karleman estimates. So we have to prove new Karleman estimates for the non-homogeneous adjoint problem. It is known that the key to prove Karleman estimate is to define good weights. In particular, in this case, we consider the function phi, which is the product of theta and psi, where theta is this function and the psi is defined in this way. C1 and C2 are positive constant, but C2 is chosen such that this term, the function psi is negative, okay? This function psi is negative. And this is important since if we define WV as the product of V times the exponential function, we have that WV satisfies this equation. So we have the same boundary condition as before, but we have this additional condition at time t and at 0. And we prove this fact since the function phi in this case is negative. So, okay, so now the idea is to rewrite the equation satisfied by WV as an equation of this type, where so LIS is this operator and LI is this other operator. Using the idea then is to rewrite the operator LIS as the sum of the self-adjoint part and the skew-adjoint part. In this case, the skew-adjoint part and the self-adjoint part are given by these formulas. I recall you that I equal to 1 is the non-divergence form, I equal to 2 is the divergence form. And so, using this equation and rewriting the operator in as the sum of two other operators, we can consider the norm on the Hilbert space, L2 or L2 with the weight, the norm square. So we have that this term is given by this norm square plus this norm square plus 2 times the product. And so we have that 2 times the product is less or equal than this norm. And from this inequality, we can obtain the Karleman estimates. So it is important to compute this product. And when we make the computations, we have some distributed terms plus some boundary terms. The distributed terms are the following ones. So as you can see, there are a lot of integrals. And so for I equal to 2, so for the divergence case, we have these other integrals. Clearly, these integrals, the distributed terms are different from the distributed terms that we have for the autonomous case, since here, first of all, we have these additional terms. So we have the derivative of rho 0, and in these integrals, we have clearly this function. For the distributed terms, we have, in any case, we can estimate from below the distributed terms by the sum of these two integrals. If in the autonomous case, we do not have this function rho 0 square. For the boundary terms, we have, in the non-divergence case, we have only this term, and for the divergence case, we have only this other term. And thanks to the boundary condition, we can prove that the boundary terms just are equal to an integral, a very simple integral. And so using the previous inequality, we can prove that the function WV satisfies these two estimates in the non-divergence case or in the divergence case. Now, recalling that WV is given by V times the exponential function, we can obtain the Karleman estimates for V, which are the following one. And so, thanks to we can prove using cutoff function the observability inequality, and thanks to the equivalence between global null controllability and observability inequality, we can obtain the global null controllability. Just a remark, we have from the previous Karleman estimate, the observability inequality that we obtain is this one. Is this one for the non-divergence case and this one for the divergence case. But clearly, if rho is a continuous function, so it's E has a minimum and a maximum, and recall that it is strictly positive. So using this property, we can obtain exactly the same observability inequality that I wrote you before, and that are equivalent to the global null controllability. So we obtain these results if for the previous model. Clearly, this global null controllability can also be extended to the case when A degenerates at both boundary points using just cutoff function. We can prove Karleman estimates if here we add a linear term. So when it is enough to require that C is a bounded function, so we can obtain global null controllability for this equation. And using this result and the fixed point theorem, we can prove global null controllability also for a semilinear problem of this type. In this case, the function h satisfies the following condition. If we come back to the Boudico-Seller model, we have that the function h is this quantity. So Re, I recall you, is the energy emitted by the Earth. Ra is the energy absorbed by the Earth. So Ra is, I recall you, the product of Q times beta. Q is bounded in this case. Now, if we require that beta is non-negative, Lipschitz continuous, such that beta at 0 is equal to 0, and if we consider this particular case, we consider the Boudico function with a equal to 0, then we can prove that the function h satisfies the previous assumption, so we can apply the global null controllability results. Clearly, there are some open problems. So, what happens if rho 0 is 0 somewhere? For example, it is important the fact that rho 0 is strictly positive. It is also important to prove a global null controllability under more general function h. For example, we cannot apply the previous results if beta at 0 is not 0 or a is not 0, or if we consider the Seller model, so if we consider the Stefan-Boltzmann law. And it would be also interesting to study the more general case when A depends on T and X. I recall you that this definition is very helpful since we have that the domain of the operators are independent of T. In this case, we don't know. Perhaps we have to add as assumption, okay, or require something more. But now I'd like to consider another problem. As you know, one of the biggest problems this year is the global warming. So how can we solve this problem? An idea is to increase the amount of energy reflected into space. And a suggested strategy to obtain this result is by coating it with a small proportion of particular materials called passive daytime radiative cooling materials. They can be found in many forms, such as glass polymer hybrid metamaterials or porous polymer coatings. And these materials don't just reflect the sun rays back, but they are highly reflected and highly emissive at the same time. Moreover, they emit more energy than they absorb, and a part of this energy can bypass the Earth greenhouse and send the sun heat back into space. And to model this phenomena, Hahn and Odzisik impose Robin boundary condition in heat transverse problems. These conditions are indeed called also radiation boundary condition or convective boundary condition. And for this reason, we consider the same problem, but if A is weakly degenerate, we consider not the Dirichlet condition, but the Robin boundary condition, which are this one if the problem is in non-divergence case, and this other one if the problem is in divergence case. If A is strongly degenerate, we obtain exactly the same condition as before. Here, the parameter beta 0, beta 1, gamma 0, and gamma 1 are satisfies this condition. Clearly, if beta 1 is 0 or gamma 1 is 0, we have exactly the Dirichlet condition as before, so it is not interesting in this case, in this sense. There is a paper that considers also the Robin boundary condition. It's the paper of Floridia. Floridia considered multiplicative control, the autonomous case, and only the divergence case. In our paper, we consider the interior control, the non-divergence case, and for both cases, we consider the non-autonomous case. And so another difference, but very here Florida consider -1, 1. Okay, so the degeneracy points are -1, 1. Okay, yeah, there is just a misprint, is -1, not 0, sorry. Okay, so in this case, clearly the Hilbert space are different from before. For example, in the non-divergence form, we have the same space as before, L2 1 over A, but H1 1 over A and H2 1 over A are different since here we do not have the condition, the Dirichlet condition at 0. Okay, the boundary condition at x0 at the degeneracy point can be found in the domain of the operator. Using the semigroup technique, one can prove again that the operator generates a contraction semigroup and the domain is dense in L2 1 over A. For the divergence case, H1A is different from before. Again, here we do not have the Dirichlet condition. We find again the boundary condition in the domain of the operator, and again we prove that the operator generates a contraction semigroup. So using these new spaces, this condition under this additional assumption. I recall you that A is weakly degenerate, and using the assumption if A is weakly degenerate, one can prove that 1 over A is integrable. So this term is well defined, and this estimate is very important since as for the autonomous case, one can prove that the global null controllability is equivalent to the observability inequality only if the previous this inequality holds. So we have the equivalence between a global null controllability and observability inequality only under this additional condition. Okay, so they are very, very important in this case. As before, to prove the observability inequality, the idea is to use Kahneman estimates. So one has to compute again the Kahneman estimate, which are different from the previous one. The idea is clearly the same. So we rewrite the equation of the joint problem in this way. Then we rewrite this equation using this equality. We rewrite this operator as the sum of the self-adjoint part and the skew-adjoint part. We compute the product. The distributed terms are the same, but the boundary terms are different, since we do not have, as before, the Dirichlet boundary condition, but we have the Robin boundary condition. So these, for example, these two terms are no more equal to 0. Okay. Anyway, we have that this term, the last integral, in both cases, is positive, thanks to the assumption on the function A, the assumption that we found in the definition of weakly degenerate function. And so we can estimate the boundary terms from below using the sum of the first two integrals. So for the divergence case, we have these other boundary terms. Again, the last integral in both equality is positive, so we can forget it. And then we can prove that WV satisfies the following two estimates. Okay, here now we have this integral, and we have to estimate this integral. And we can do this thanks to the fact that rho 0 is a positive continuous function. So the minimum is strictly positive, and we can estimate this term by these other terms. So we can absorb this integral with the first integral, the first integral that we find on the left of the inequality. The same for the divergence case. We can estimate this term in this way, then we can absorb this term by the first integral. And these are the two inequalities that if the degeneracy point is 0. If the degeneracy point is 1, clearly the estimates are different but similar. Here the only difference is that we have gamma 0 and gamma 1 that are the parameters that appears in the Robin boundary condition if the degeneracy is at 1. In any case, we can absorb this term by the first integral in the left. And so, thanks to the previous Karleman estimate, we obtained observability inequality, and hence the global null controllability also for the Robin boundary condition in the weakly degenerate case, if this condition holds. This condition comes from the fact that we have to estimate these two terms, okay? So clearly, if we have the Dirichlet condition, this term, the boundary term, are 0, so we do not have this problem. So also for this case, we have some open problems. Here we can, it is important also in this case to study the global null controllability if rho 0 is 0 somewhere. Also in this case, it is important to consider the more general case, and it is also important to study global null controllability if beta 1 or gamma 1 belongs to one of these two intervals. So I recall you that this is a technical assumption, okay? So probably using another technique, one can prove that the estimate on the solution still holds, and so one can prove that the equivalence between global null controllability and observability inequality holds without requiring that beta 1 is strictly greater than this term or gamma 1 is strictly greater than this other term. And just to conclude, some work in progress. We are now studying the previous problems with a delay or a memory term. And we are also considering these two operators. So clearly they are more general than the previous one. Only the autonomous case. We are considering only the autonomous case. There are no results if A degenerates somewhere. We have some results if A is strictly positive and the P is greater or equal than 2, but just on existence or uniqueness and so on. But no results if A degenerates somewhere. So that's all. Thank you for your attention.
Professor Fagnelli, thank you very much. This was a really nice talk. Does anyone have any question or remark for Professor Fagnelli? Okay, maybe you can share one question. This is probably connected with something you mentioned at the end of your talk, but still, I would like to ask this. So, when you introduced these boundary conditions, you mentioned that for, not really sure about this part, but when you have this weakly degenerate part, then you assume Dirichlet boundary condition, and then for the other one, you assume the Neumann condition, right?
For the first part.
Exactly. So is it meaningful to consider the problem in a reverse way, meaning that you consider Neumann condition for the first problem and Neumann for the other one? Is this possible?
So there are also some results when A is weakly degenerate, one consider Neumann boundary condition. Yeah, there are. The most natural one is the Dirichlet, but there are some results. If A degenerates at the boundary and if A degenerates in the interior.
Okay, perfect. Are there further questions, maybe? Yes, Duvan, please.
Okay, Jenny, thank you very much for the very nice talk, of course. No, I have two questions, right? Maybe I don't know if my question makes sense, right? But let's say for Kahneman estimates, there is a classical condition, right? The subelectricity condition by Hormander. And one is working, let's say, with the Laplacian, right? And remember, I just wanted to know if at some point when you are proving this, your Kahneman estimates in your model, you have to deal with this condition at some point, or if it's not required for your analysis?
No, for our case, we can prove directly Kahneman estimates.
Directly, okay. This was first. And second, maybe more related with respect to the literature, right? There are some works also about controllability where the open subset, where the subset omega is not open, but one replaces it by one measurable set. If you consider this problem also, when you have control, but with the internal region omega not to be open subset, but measurable set.
No, in general, I think that there are only results when it's open, not only measurable.
Okay.
Since you need that omega is compactly contained in 0, 1 if the control is in the interior.
Okay.
Okay. Clearly, if it's the control region is all the domain, there are to prove that.
Okay, very nice. And last question is the picture the picture in this slide your university or the station in Siena? Because it looks like the
Campo in Siena.
Because it looks very similar to the station of Ghent.
No, It's very
Train
fast.
station.
Right. Okay.
It's one
thank
of
you.
the most places in Italy. It's Piazza del Campo.
Thank you very much.
You have to come to in Siena.
For sure. Thank you, Jenny. Thank you very much.
So there is one question on the chat, but I think we don't have much time left. So I suggest I will just save the question and maybe we can continue. So thank you very much to our speaker for this engaging talk. And then we continue with the last lecture from today's schedule. Thank you very much.
Okay. Good morning, good evening, good afternoon, everyone. It's a great honor to introduce Dr. Marco Antonio Pérez de la Rosa, a distinguished academic and full professor at Universidad de las Pueblas, Universidad de las Américas Puebla. Today, he will present his talk titled on the Moisil-Theodorescu operator in fractional settings and in curvilinear coordinates. Please, Dr. De La Rosa, the screen is yours.
Thank you very much. First of all, I want to thank the organizers for allowing me being here today and to talk to you about the very important operator called the Moisil-Theodorescu operator. And in fact, is considered as one of the most important generalizations of the Cauchy-Riemann operator from one-dimensional complex analysis. One of the reasons for that is that it's a square root of the Laplace operator in R3. So in this talk, I will try to give a brief account of what we produce in these three papers together with my colleagues, the Professor Juan Boris Reyes and Yudier Peña Pérez in these three papers. So as I will talk about the operator in a quaternionic setting, it is important to give you a brief account of what is quaternionic analysis, okay? So first of all, I will define an element in H, in here, or in H of C, as a linear combination of these quaternionic units, okay? So I0 will be written as the real number 1, I1, I2, and I3. That the three quaternionic imaginary units satisfy these multiplication rules that you can see here. All of the three imaginary units satisfy that to the power 2, we obtain -1, and they satisfy these rules of multiplications between them. If you consider in the coefficients real numbers, you have what is called real quaternions or only quaternions as usual, but also you can consider coefficients being complex numbers, in which case we will by definition say that the complex imaginary unit I commute with all the quaternionic imaginary units I1, I2, and I3. So with these rules, the real quaternions form what is called a skew field, as the only property that are missing, or is missing, is the commutativity due to the multiplicative rules that I presented in the middle. But for the case of the coefficients being complex numbers, you have also zero divisors. So you only have a non-commutative algebra with zero divisors. We have in here several representations in general for a complex quaternion. As we will see in the previous slide, you can represent it as a linear combination of the quaternionic imaginary units, or also in this form where the A's with super indexes are real quaternions. So later I will call this the real part of the complex quaternion, or B quaternion A, and A with superindex 2, we will call the imaginary part, okay? So another very useful notation for quaternions or B quaternions is the following. If you called A0 the scalar part and the linear combination of I1, I2, and I3 vector A, or A with an arrow, you can form a real quaternion or a complex quaternion. as this sum of scalar and vector parts. With this notation, you can have that the product of any two quaternions or biquaternions can be represented as this sum of elements, in which you can observe all the scalar and vector operations in one. So in here we have the product between two scalars, the product of a scalar by a vector 2 times. Also, this sum of the products of the entries, that if you have real numbers, is the scalar product in R3. And in here, this part that can be computed as this determinant in the case where we have real quaternions, it can be considered the cross product. So this is a very good first step, in which you notice that all the vector analysis is inside the quaternionic one, okay? So a main involution can be defined on the real and complex quaternions, called the conjugation. The quaternionic conjugation will be denoted by this bar. By definition, you have only to change the sign on the quaternionic imaginary units, okay? Next, with these conjugations, if you perform the product between two biquaternions, you can represent this as this sum of the product of the coefficients with themselves. And also you can have these two really similar representations. And one important thing here is, first, this product will give always a complex number. But in the case where you have a real quaternion, means that the imaginary unit will be 0. And in that case, you will have the Euclidean norm in R4. For the case when you have this, the real and imaginary parts being orthogonal in this sense, you will have that in the case that the real and the imaginary part, if they have their real norms equal, then this product will be 0. So with this help, as I mentioned before, you can characterize the 0 divisors in the set of the complex quaternions. But in fact, you can also define the Euclidean norm in C4 with the help of another conjugation, the complex conjugation. If you take the scalar part of the biquaternion with its quaternionic and complex conjugate, you will obtain always a real number. And also you can define like this the semi-norm in C4. So in here I will define with this symbol the elements in the biquaternions that are 0 divisors. If you have a biquaternion that is not in this set or is not 0, then the inverse element can be computed by only taking the quaternionic conjugate over the product of its quaternionic conjugate. So this allows to define for every element that is not a 0 divisor or 0 and multiplicative inverse. Also, it's worth noticing that the set of all the invertible elements are all the biquaternions minus this set. Okay, so in which I will use different notations. In order to consider all of them, I will define the first one. If you have a domain in R3, you can consider functions that are valued in the set of biquaternions in the 4 following forms. In here, as a linear combination of the quaternionic imaginary units, in which all the component functions go from the same domain, but they take values on the complex numbers. In the second notation, remember that is the complex notation, you will have that the component functions will begin in the same domain in R3, but they will take values in the real quaternions. And in the third notation, you will have the scalar part that takes values on the complex numbers, and arrow F will take values in C3. Okay, now we are ready to define the important object of the study, that is the Moisille-Theodorescu operator. It will be denoted like this, and it's simply this really interesting operator. And I will talk about some interesting properties during this lecture, okay? So, as I mentioned before, one important property is that it is a square root of the Laplace operator. So, the quaternionic function theory for the Moisille-Theodorescu operator shares a lot of important properties of the holomorphic function theory of one complex analysis. And also, we have a similar factorization, okay? So, the functions that belong to the kernel of this operator will be called hyperholomorphic functions in analogy to the holomorphic functions for one complex analysis. So, one of the most important properties that we will use today is that if you have the quaternionic function represented in the third form that I presented before, then the action of the Moisille-Theodorescu operator can be represented as the sum of these three very well-known operators in vector analysis: the divergence of its vector part plus the gradient of the scalar part plus the curl or the divergence of its vector part. So this operator, it has very well-known acting on the set of the real quaternions or complex quaternions if you use the Euclidean coordinates, but we noticed that it was not the fact for the case of any orthogonal curvilinear system. So this is why we decided in the first work to work with the Moisille-Theodorescu operator in a general orthogonal curvilinear system. Okay? First of all, in here, we will let x, y, and z represent the Cartesian coordinates in R3 with the corresponding orthonormal bases I1, I2, and I3. In here, we will assume, as always, that Q1, Q2, and Q3 are general orthogonal curvilinear coordinates defined via three invertible and continuously differentiable transformation functions. So in here, x, y, and z will be three new functions of three new variables, Q1, Q2, and Q3. So it is really well known that each system is characterized by the metric coefficients hi, or I running from 1 to 3. If you compute these metric coefficients, you can define the new basis that I will denote by ui. In here, the new ui's are defined like this, where I also runs from 1 to 3. So I'm using the notation again. If we take a quaternionic valued function, instead of writing it as scalar and vector part, sometimes you can rewrite it as, again, the scalar part, but the vector part will be denoted as a linear combination of the elements in the new basis. Okay? With this in mind, as usual, you can define the gradient of the function the scalar part, the divergence in any orthogonal curvilinear system like this, and the curl or the rotational of the vector part like this. These three operators can be found in any book that talks about orthogonal curvilinear systems, okay? But in fact, in here, as I presented before, you can connect all these three operators in only one by the help of the Moisel-Theodorescu operator. So, as we mentioned before, the Moisel-Theodorescu operator can be defined as minus the divergence plus the gradient of the scalar part plus the curl of the vector part. And in any orthogonal curvilinear system can be written as this sum. So in here, I will define a new Laplacian that will be the action of two operators. Each of them will be acting on a different part of the quaternionic function. The first one, a lambda, capital lambda 0, is the scalar Laplacian, and the second one with the arrow is called the vector Laplacian. The scalar Laplacian, as usual for scalar functions, is defined as the divergence of the gradient. So it is easily computed like this by the composition of the given previous formulas. The operator that is not very well known, as I will explain you later, is the vector Laplacian that is defined as the gradient of the divergence of a vector part and the curl of the vector part. So in general, curvilinear coordinates, it can be written like this. So in here we have only the U1 component, and in this slide, the U2 and U3 components. It is usual that the action of the vector Laplacian is replaced by the action of the scalar Laplacian acting on each component. But as we will show you, this is only happening for the case of the Euclidean coordinate system. So for Cartesian coordinates, you have that the metric coefficients will be each one h2 and h3 equal to 1, and the new units will coincide with the previous one. So the Moisel-Theodorescu operator can be written as this sum of operators, and the scalar Laplacian is, as usual, this very well-known operator. The vector Laplacian is written using the previous formulas like this. So I will stop in here and let you notice that with this equation, we can get the wrong idea that the vector Laplacian is the action of the scalar Laplacian component by component. But as will you notice, when you use, for example, spherical coordinates defined like this, for r, theta, and psi, then the metric coefficients are well known to be 1, r, and r sine of theta, while the unit tangent vectors to the orthogonal coordinate curves are u1, u2, and u3 like this. So now we define the Moisel-Theodorescu operator in spherical coordinates, and it takes this form. You can define also the scalar Laplacian using the previous formula, and this is the very well-known scalar Laplacian in spherical coordinates. But now I want to show you the vector Laplacian in spherical coordinates. If you notice, please pay attention only on the first component. It can be seen that all these terms appeared in here apply to F1, But also, we have the final three terms that are different to the action of the scalar Laplacian. So with this, we have proven that in general, the vector Laplacian is not the action of the scalar Laplacian in every coordinate. And this is why you have to define a quaternionic Laplacian like this. This action is the scalar Laplacian over the scalar part and the vector Laplacian over the vector part. And with help of the standard differential operators, you can define every of the operators in every orthogonal coordinate system. Okay? So I will continue with one of the application of this theory. So it turns out that the enormous success and large application of local and non-local fractional calculus, for example, you can refer to the works of Yang, is a strong motivation to show its connection with quaternionic analysis. In particular, the main goal of the second paper that I will present to you is to develop a quaternionic structure for the local fractional Moisel-Theodorescu operator in Cantor type. It was done in cylindrical and spherical coordinates, but in here I will present to you only the spherical case. So first, you have the following definition. Let f be a function defined on a fractal set of a fractal dimension alpha with alpha between 0 and 1. The function f is said to be local fractional continuous at x equal to x0 if for each epsilon greater than 0, there exists a corresponding delta greater than 0 such that the distance between these two numbers is less than epsilon to the power alpha whenever the distance between x and x0 is between 0 and delta. Next, the local fractional derivative of f, in this set I will define later, of order alpha, remember alpha between 0 and 1 at x0, is defined like this. We will use the operator notation or also this limit in which you can define like this the Laplacian to the power alpha to be the Euler's gamma function of 1 plus alpha multiplied by this difference, where this gamma function is defined as usual. So the set of all functions that it is local derivative exists for all x on the interval AB will be denoted like d alpha. The set d alpha is called a alpha local fractional derivative set. So examples of generalized functions defined on Cantor sets are given, for example, the analog of the exponential like this, as this sum, and also the sine and cosine functions on a fractal set are given respectively by these definitions, by using this generalization of the Euler's function or exponential, or in terms of sums like this, where in here x belongs to the real numbers, alpha between 0 and 1, and I alpha is an imaginary unit of a fractal set. Okay, now, as Yang defined, we can consider the Cantor set, the Cantor type spherical coordinate as follows, defined in a similar way as before, but in here with functions defined like this. Okay, in here you can define a new basis given by ER alpha, E theta alpha, and E psi alpha as these combinations of the new basis. If you have a scalar function Yang defined the gradient of F0 as this new operator in terms of the counter-type spherical coordinates. Also, if you have a vector value function, then you have its generalized divergence and its generalized curl defined like this in a similar way as before. So next, we can link the theories, and now with the help of the structure of the Moisel-Theodorescu operator, we were able to define the Moisel-Theodorescu for counter-type sets as follows: minus the divergence again of the vector part, plus the gradient of the scalar part, plus the curl of the vector part. So now you have a function theory defined for the Moisel-Theodorescu operator for functions in counter-type coordinates. In this particular case, the spherical ones. But as I mentioned to you, there exists a version for cylindrical coordinates. Also, the local fractional Moisel-Theodorescu operator factorizes the Laplacian as follows. If you apply 2 times this version of the Moisel-Theodorescu operator, you obtain minus the Laplacian in this theory, where, as before, we define the quaternionic version of the Laplacian as the action of the scalar Laplacian on the scalar part and the action of the vector Laplacian of the vector part. Again, the scalar Laplacian is the composition of the gradient with the divergence, and the vector Laplacian is this difference of this composition of the previously defined operators. Okay, in here you can see that the scalar Laplacian in spherical on counter-type spherical coordinate takes this form, and the vector Laplacian in counter-type spherical coordinates takes this form. You notice that again, the action is different to the action of the scalar operator on each component. Okay, so also in the third paper that I presented in the first slide, we talk about another version of the fractional Moisel-Theodorescu operator. It turns out that a mathematical formula to construct the fractional operator corresponding to a given linear one has been a subject of numerous studies. For example, Enguera developed the concept of a fractional curl operator, and it was the first one that proposed it. So following the technique that defined Enguera, we explored in our paper a novel factorization of the Moisel-Theodorescu operator, which will be obtained after doing the same for the divergent and the gradient operators. And it's worth mentioning that the obtained operators also can be considered good generalization of the classical ones, as they can be obtained with special values of the parameters that I will introduce next. And also, it's important to mention that because of the first order approximations, the fractional differential operators that I will present in this work are valid only on a far-field region, okay? So let me begin with these definitions. So in a d-dimensional fractional space, the integration of a radially symmetric function f of r is given by this equality, where r of x1 and x2 represents the distance between 2 points x1 and x2, and capital W represents the weight. The weight is defined also through another function of the parameter d, that is the dimension, that is defined as 2 pi to the power d over 2 over the gamma function of d over 2. Okay, So with the work of Suber, Mugar, and Nagby, the Laplace operator in d-dimensional fractional space in 3 spatial coordinates can be represented in this form. In here, the measured distribution of space is described by the 3 parameters di, with I running from 1 to 3, each acting independently on a single coordinate, and the overall dimension of the system is the sum of the 3. If you notice, if the parameters d1, d2, and d3 are equal to 1, we obtain exactly the 3-dimensional Laplacian operator, and in here also the dimension will be the sum of 1 plus 1 plus 1, there is 3. So everything is correct, and it turns out that with the help of the work that I just mentioned, for the far field, that it will be represented like this, the Nabla operator in fractional d-dimensional space is defined as follows, in which the variables x, y, and z with hats represent unitary vectors in the direction of the standard vectors, and these operators are defined to be the partial derivatives with respect to the stated variables. Okay, so with the help of this Nabla operator acting on a scalar field, we can define the generalization in this theory of the grading operator, and will be defined like this. Also, we will act this Nabla operator as this operation on a vector valid function, and we will obtain the analog of the divergent operation for far field. Also, with this action, we can obtain finally the curl operator in this theory. And also, you can notice that if you again use d1, d2, and d3 being equal to 1, you obtain again the standard grading divergence and curl operators. So, with this in mind, and the previous decomposition of the Moisille-Theodorescu operator, you can define the generalization of the Moisille-Theodorescu operator for far field in terms of the previously defined divergence, grading, and curl operators. And if you have a quaternionic or biquaternionic Polich function, you can have this operator and also construct the version of the quaternionic function theory for the version of this operator in this setting. Again, we have that the Laplacian operator can be factorized as the action of the Moisille-Theodorescu operator in this theory with itself, where again you can define the scalar Laplacian and the vector Laplacian as acting again on the scalar and vector parts respectively, and the scalar Laplacian defined as the composition of the divergence and the gradient, and the vector Laplacian as the difference between the compositions of gradient with divergence and the curl with itself. Okay, if you want it, you can see the action of the scalar Laplacian in this setting for far field for a scalar valid function, and it takes this form. For the vector Laplacian, you have now this form, and also is worth mentioning again that both operators, the scalar and vector Laplacians, the standard ones, can be obtained again by setting D1, D2, and D3 equal to 1. So with this, I finish my talk, and I want you to notice that with the help of a quaternionic operator that defines the hyperholomorphic function setting, you can extend, as we did in these two papers, to the case of Cantor type coordinates, or in this case, for the dimensional spaces in far field. So thank you very much. This is all.
Thank you. Okay, can you hear me well, sir? Okay. Okay, thank you so much, Dr. Perez de la Rosa, for this insightful presentation.
Thank you.
We now open the floor for questions. If you have any question, please feel free to use the raise hand feature or type in the chat. Okay, Professor Duban, please go ahead.
Thank you, Tobias. Professor Marco Perez, thank you very much for your very nice talk. That's
Thank
very
you.
interesting, of course. I just have a question about the way in which you define your fractional Moisille-Theodorescu operator, right? Do you define it using the spectral theory? I mean, as a function of the spectral resolution for this operator, or does it coincide with the definition using a spectral theory, or?
Okay, it's in this version of in Cantor type coordinates.
In this version.
Okay, so in this version, we only took the advantage of the operator, the Laplacian operator defined by Subair, Mukhag, and Nadby. And in fact, they use a trick to rewrite the Nabla operator in one dimension, and then they extended the procedure to 3 dimensions, and they managed to define this operator, the Nabla operator, for far field. So if you want, I can share with you the paper where we talk about the development of this operator.
Okay, thank you very much. Okay, now it's clear for me. And maybe second question, but it's more a philosophical question, right?
Yeah.
Because in your setting, you show that this operator, your Moisille-Theodorescu operator, is like a square root of the Laplacian, So one can take in the Euclidean setting like a Dirac operator, right? Dirac type operators that are.
Exactly.
So how much they have, does they have similar properties like the Dirac operator, or similar spectral properties, or
okay. Yeah, thank you very much. So in these two versions of the theory, we only defined our Moisille-Theodorescu operators. So we stopped there and we didn't deepen in the theories. But once you get this factorization of the Laplacian or the Laplace operator, you can start with the analysis, with the mathematical analysis. For example, with the help of this factorization, you can define for example, fundamental solutions of the Moisille-Theodorescu operator with the help of a fundamental solution of the Laplacian, and define the analog for each theory of the Cauchy integral type. Okay, so what I want to mention to you is that we didn't develop the theory, but it shares a lot of connections. First, with the help of this factorization, with the traditional quaternionic analysis or Clifford analysis, or as I mentioned at the beginning, with the holomorphic function theory of one-dimensional complex case. So we only started with the factorization, but all the theory can be constructed from here.
Well, thank you very much. Thank you very much.
Thanks, Professor Duvan. Any other question? Well, I'm just curious. In your presentation, you focus on one specific definition of the fractional derivative. Any motivation to use that one, or how can the results differ or may differ if you use another different definition?
Okay. Yeah, thank you very much for your question. Okay, if you notice, all the connections we did in the couple of works that I mentioned were made through the case of theories where the traditional gradient, divergence, and curl operators are well defined. Okay, so I started with the definition of the Moisel to the rescue operator in the traditional quaternionic or biquaternionic setting. So the two connections we made with fractional calculus were for two theories in which we have these three operators well defined, as we can connect them with the Moisel to the rescue operator. And this is the main reason we only work in these two theories, because we have these three differential vectorial operators.
Thank you so much. Well, we have a couple of minutes for any other question, if you want. Okay, Professor De La Rosa, we thanks a lot.
Thank you very much.
Professor Duvan, please take your time to.
Okay, I will close the session. Okay, thank you very much, Tobias Castro, one of our organizers from Universidad del Atlántico in Colombia. Okay, this was a very nice first day in our conference dedicated to Professor Luigi Rodino. So now we close our scientific program. It's with great pleasure that then we invite you to join us tomorrow. According to our scientific program, we are going to start tomorrow at 3 p.m. in Central European Time, which will be 9 p.m. in Colombian time. So thank you very much to all of you for joining us. And then see you tomorrow. Alexandra, muchas gracias. Creo que ya podemos entonces cerrar la sesión el día de hoy.
Muchas gracias, Alexandra.